Ey, 1, 2, 3. Prueba de audio para transmisión. 1, 1, 2, 3. 1, 1, 2.
given by Satya Majumdar on stochastic resetting, so which is a topic basically that he initiated with another colleague and on which he has contributed a lot over the last 10, 15 years, maybe. Actually, there will be other talks related to stochastic resetting in this meeting, and maybe a poster, I think. So please, Satya, welcome, and go ahead.
It's up. And this one also? Okay, this, yeah, okay. So thank you, Denny, for the introduction. And And in fact, I would like to start by thanking all the organizers for the invitation. And it's my first time in Guadalajara. And so it's a pleasure to be here. Thank you very much. Okay, so I'm going to talk about stochastic resetting. Yeah. So it's a relatively sort of new area in statistical physics, about 10 to 12 years old. And but in this last decade, it has seen a lot of development, both theoretically and experimentally, and also with a lot of applications ranging from biology to computer science and many other areas. So what I decided to do today, since the organizers have kindly given me a 1 hour slot, so I wanted to give you an overview of these recent developments, and so keeping the talk at a sort of less technical level. And I also apologize to people who have heard some of this, some part of this talk before, and but I hope there'll be new things here. All right, so here's the here's the outline of my talk. Oops. This is always a problem. How does it work? Doesn't work. Ah. Hmm. Okay, so here is the outline of my talk. So I'll first start with a brief introduction to stochastic resetting and tell you why this is interesting. And then I'll discuss just one simple toy model, which will teach us quite a few things. And this is just a diffusion with stochastic resetting. And there'll be 3 new facts which will come out of this simple toy model. And then I'll talk about the recent experiments using optical tweezers. And finally, the last half of the talk, I'll talk about the generalization to many body systems, both classical and quantum. And then finally, I'll summarize and conclude. Okay. So let's start with this motivation that why we are interested in stochastic resetting. And so the first motivation actually comes from the growth of a city, population of a city. For example, here I'm showing you the New York City, Manhattan. So from 1609, and this white part, it grows. You can see that it grows very rapidly, and so any city, if you like, it grows with time and things like that. And you can also do other growth models. You can do controlled experiments, which is a growing bacteria on a petri dish. So you see these bacteria, they multiply with time, and their population grows with time. Okay. And so this population growth, can go on forever. But what happens is that once in a while, you have some, extreme events like earthquake or hurricane or tornado, tsunami, etc., which strikes a city. Or, for example, in the context of bacteria, you can just put antibiotics and kill most of these bacteria. And so these extreme events are rare. They don't happen every day. But when they happen, they occur, they have devastating effects. And in fact, they can just wipe out a population of a city. So roughly speaking, schematically, so you have this population size, which is growing with time exponentially almost. And then once in a while, these catastrophic events occur. And this is the reset, basically, which resets the population to almost, zero. It wipes out. It may be a finite number here. And then again, the population starts growing. And then again, at some random time, some earthquake happens, and then, or something like that happens, and then it goes down, it gets reset again, and it grows and so on. Okay. And so there's these 2 effects, population growth, and then this, sort of random resetting. And so they have competing effects. And one of the questions to ask is that will the population size stabilize at long times, which means that if I look at the distribution of the population size, will it become stationary at long times? Okay. And in the context of bacteria, so in the context of bacteria here, so what you see is that, basically this is an important question in medical science, because what happens is that, if you just, if the bacteria are growing, let's say in a human body or something, and then you put these antibiotics, and which kills the bacteria population, but then 1 or 2 bacteria can mutate, and then they start growing again, the population. And then again, at some other time, you put the antibiotics, and again, this happens. And so this mutation followed by the antibiotics, so it can actually, stabilize this bacterial population. And this is what is called the superbug effect, superbug population, which are become resistant to antibiotics. And it's a sort of important problem because this is the cause of death in all over the world, the biggest cause of death, the superbugs. And so people actually are interested in doing experiments to see how the superbug population stabilizes with time. Okay, so this is the sort of this question of whether there is a stationary state at long time, and if it is, how do we reach this stationary state? The second motivation comes from search problems. So as you know, search problems are ubiquitous. I mean, animals searching for food, or a helicopter searching for survivors after a shipwreck, or even DNA, protein searching for a site to bind on a DNA, and or even more mundane example, like when you are writing your computer program and you want to debug your program, looking for the bug, and so in many of these search processes, it's got a quite natural intuition tells us that maybe after a while, when you have searched in vain, you might want to just go back and restart from the beginning. And the rationale is that if you restart from the beginning, you might find a different pathway, explore a different pathway to find the target more easily. So for example, if you are looking for computer bug, it's a good idea maybe just to stop at some point, go for a coffee break, and then come back and restart from the beginning, and you might find the bug more quickly. Okay? And in fact, the psychologists, they actually do these experiments. So this is a visual search. So visual search means that you have a big crowd and you are looking for the face of a friend, let's say. So how do our eyes search for the face? Okay, it never scans from one side to another side. What it does, it starts at some random point, it searches locally, and then it sort of keeps coming back to the initial point, and then again it explores another area and so on. So in fact, as I said, the psychologists do the experiment. So they show the patient a big blackboard containing the letters P, and then they ask, so in this milieu of P, there is one B, and they ask the patient to look for the B, and they fit a camera in the eye and to look at the trajectory. And so what you see is, again, the trajectory is typically, this is a schematic trajectory. It starts from some point, and it does a kind of random walk, and it doesn't find, and then it comes back to the starting point, and then it restarts a new trajectory, okay, and so on. And in case you haven't find out where the B is, it's here actually. Okay, so anyway, so this is the sort of search problems and is very important. And in fact, the computer scientists, they have been using this. For example, if you are doing simulated handling, so for example, this is just an energy landscape. So this, the horizontal axis are some configurations, and this is the energy of a configuration. For example, in glassy systems or any other disordered systems. And typically, you look for the minimum energy configuration. That is the ground state of this configuration. So what you do, you start from some point here, and then you make some local moves, like you update a spin or move a particle, and then you move in this configuration space from one configuration to another configuration. And then the problem is that that if you're at low temperature, you might actually get stuck in a metastable configuration for a very long time, and it will take long time to cross over this barrier and to reach the real ground state. So to avoid that, what you can do is from time to time, so if you are not finding it, you just go back to your starting configuration and restart the search process. And when you restart again, the rationale is that you might find a different pathway and might reach the the global ground state much more quickly than if you don't do the resetting. Okay? So this is these are the sort of motivations. So one question in the context of random search problems, therefore, is that does the stochastic resetting, from time to time, does it help really in searching the target? Does it really reduce, for example, the mean search time to find the target? Okay. So this is the sort of the motivation from the search problems. That so to summarize, there are two principal issues when you have stochastic. So stochastic resetting simply means that you have a system with its own natural dynamics, and you interrupt at random times and go back to the starting configuration, and then you evolve again. Okay. And so the two main questions here is that first, does the system reach a stationary state at long term? And second is that does stochastic resetting make a random search process efficient? That means you find your target in a lesser time. Okay. So these are the two questions, the main questions. So what we wanted to do is about 10, 12 years back, 13 years back actually, is to study these two questions in a context of a very, very simple toy model. Okay. And that's what I'm going to describe to you now. And so this is the work which was done with my colleague Martin Evans from University of Edinburgh. And so this is just a simple model of diffusion with stochastic resetting. So let me define this toy model for you. So the model is very simple. So I'm just defining it in one dimension for simplicity, but you can easily generalize to higher dimension. So I have this space and time, and I have just a Brownian motion which starts from initial position x0, and it just does diffusion, okay? And then after a random time, which is distributed exponentially with parameter r, so you just go back to your starting position x0, and then again you restart. So the green part is just the diffusion, and then again this red part is the resetting with rate r. Okay? So that's the model. So more precisely, if you're doing computer simulation, let's say, continuous time dynamics, so in a small time interval delta t, you update your position, x, the position at time t plus delta t, is either go back to the initial position x0 with probability r times delta t. R is the rate and delta t is the time interval. So this is the resetting, r delta t is the probability. And with the complementary probability 1 minus r delta t, you just update by, just do diffusion. That means add a Gaussian white noise with it, with the d is the diffusion constant. Okay, so that's the simple model. So if you set diffusion constant to be, let's say 1, then r is only the parameter, the resetting rate, essentially. Okay? So first question we ask is what happens to the position distribution? Does it reach a stationary state? Okay? So note that in the absence of resetting, when r is 0, all of us know that the position distribution is time dependent and is just given by a Gaussian, which is centered around its initial position x0 and with width, which is square root of t. So you start from this initial position. So now the question is, if I switch on the resetting rate r, what happens to this position distribution? So the answer is actually very simple. So let me just take, this is the only technical slide in my talk. So essentially what you can do is very simply, write down a Fokker-Planck equation. So PR of xt subscript r is in the presence of resetting with rate r. So when you write down the Fokker-Planck equation, so there's a term which is the diffusion term, of course. And then with rate r, you are going away from the position x to x0. So there's a loss term, which is minus r PR of xt. And then there's a gain term, because if you are at somewhere else, then by resetting, you come back to x0, but you come back only to x0, so therefore there's a delta function at x minus x0 with rate r. And so this is it. These red terms here are the resetting terms. So without them, you just have diffusion. And you have this, you have to start from this initial condition, which is delta of x minus x0. So this is a simple linear equation with a source term, so you can easily solve by Fourier transform. I'll not go into the details. But the solution, the exact solution at all time t, you can write in a sort of very suggestive form, which is a sort of renewal approach. And let me explain to you. So you can show that this solution, exact solution at all time t, so there are two terms to it, okay? So the first term is just e to the power minus rt times the bare propagator, that means without resetting, so this is just a Gaussian propagator, p naught of xt. And then there's this term. So how do you explain this? So first term corresponds to, so think of your configuration. So you are going from x0 to x at time t, and it could be that there is no resetting at all in this interval. The probability for that is just e to the power minus rt, because this is just a Poissonian process. And in that case, the propagator is just p0 of xt, no resetting. Okay? So this is the first term. And then you might have a situation when there's one or more resettings. So in that case, what is nice is to look at from time t, you go backwards in time and you locate the time at which the last resetting took place. Okay, so let's say this is the point, and let's call this time tau. Why am I looking at last resetting? Because you don't care what happened before that, because by last resetting happened here, that means you are already at x0 at time tau backwards, and then it's just a free evolution. So this p naught of x tau here is a free evolution from the time of last resetting to the current time t. Okay. So this is just this guy. And then you have to make sure that there is no resetting in this time interval tau. And probability for that is just, e to the power minus r tau and followed by one resetting event, which happens with r d tau. And then you have to integrate this tau from 0 to t. It can be anything between 0 to t. So that's it. You can check that, by substituting in the Fokker-Planck equation, that this is indeed the exact solution of your equation. And it has this nice renewal interpretation. And this is very important because this will keep coming back later on, you'll see. Okay. So the main point here is that you have to somehow identify the right variable, which is this tau, which is the time since the last resetting. Okay, and now you have this exact solution. So first thing you look is if you take the t goes to infinity limit, this term drops out, and if this integral exists, and in this case it does, I mean, if you just do this integral trivially, I mean, it actually becomes time independent, and it has this, the double exponential form, okay, with a length scale which is the square root of d over r. Okay, so this means that so we have a stationary state solution in this simple toy model, and as I said, there's a length scale which is set up, which is square root of d over r, 1 over alpha naught, and now this stationary state is, however, a non-equilibrium stationary state. So it looks like this. So it has a cusp. It's not a non-Gaussian. So it has a cusp here as minus mod x minus x naught, and it decays exponentially as you go away. Now this one is a non-equilibrium stationary state. Why non-equilibrium? Because you have the stationary state, but in this stationary state there is always a current, probability current in the configuration space. Okay, so the detail balance is manifestly violated by the resetting move, because by resetting you can go from any point to x naught, but you cannot come back. Okay, so it violates the detail balance, which means that in the in the configuration space there will be probability, non-zero probability current. So even though this looks like an effective Gibbs state with an effective potential which is mod x minus x naught, it is actually a non-equilibrium steady state and not an equilibrium one, because the detail balance is violated. So this was our prediction 12 years back, and then more recently. So this was actually verified in the experiments using holographic optical tweezers by the group of Yale Reichman at Tel Aviv University. And I'll come back to the experiments later again. And but this was just a simple verification of this theoretical prediction. All right, so this is the question of stationary state. And now you can ask, actually, how do we approach to this stationary state as time goes? Okay, and what we'll see is that there is a sort of very unusual temporal relaxation. And to see this, I mean, all we have to do is to, you have this exact solution. Oh, sorry. You have the exact time-dependent solution here. So you just have to analyze it for example, for large t. So for large t, you can drop this term and just analyze this guy just using saddle point, just putting this form here and just do a saddle point for large, but not infinite, but large t. And what you find is that, so this is, I'm just plotting PR of xt in the space-time diagram. So this is the space centered at x naught, and this is time. So what you find is that there is a light cone here. By light cone, I mean, basically there are two regions. So there's a purple region and there's a blue region outside. So what you find is that if you are inside, so there's a length scale here, which is psi of t, which grows linearly with time with the speed square root of 4 dr. Okay. So inside this regime, if you are inside the light cone, that means if you are, so let's fix time t here and just scan as a function of x. So as long as you are inside this light cone, the solution is actually independent of time t. It's already achieved this stationary state. But all the dynamics is going on, around this light cone and in the blue region. So there it's still time dependent. Okay, and so this means that there's a time dependent length scale over which the non-equilibrium stationary state is established, and this length scale grows with time as time progresses. So that means the nest gets established on longer and longer length scale, if you like, and indeed to see what happens exactly here, as you go from the stationary regime to non-stationary regime, you can just analyze your result, just by zooming in this regime, and you can actually write the solution there in a sort of nice large deviation form, which means that you write down exponential minus t into some function of x minus x naught absolute value by t. Okay, so this is a behavior close to this border of the light cone, and this function f is actually linear for u less than u star, and then for u bigger than u star, this is the speed basically, it becomes a quadratic. Okay, and so linear means that when it's linear, the t cancels and you see that it becomes stationary state here, but beyond that, on this regime, there's still dynamics going on. So that means basically this light cone, it divides your trajectories. It's like a separatrix. It divides the trajectories into two classes. The trajectories that are inside the light cone, they undergo many resetting and therefore achieve this stationary state. Whereas those outside, there's still very few resettings, so they are still time dependent. Okay, and moreover, this large deviation function, you see the second derivative of this function is discontinuous. The function is continuous, its first derivative is continuous, but second derivative is discontinuous. So in some sense, this is a second order dynamical phase transition in this time-dependent relaxation to the stationary state. So the stationary state really gets established on a longer and longer length scale, and there's an unusual phase transition, dynamical phase transition here at this light cone essentially. So this was the work which was done in collaboration with Sanjib Sabhapandit, who is here, and Gregory shared some time back. All right, so we understand the stationary state and the relaxation to the stationary state. So now I'll go back to this second question that I posed in the beginning, that is the problem of target search. Okay, so first passage properties. So now imagine that again, I'm talking about in one dimension, and suppose that you have a fixed target at the origin, and your searcher, it starts at x0, and it wants to find the target. Okay, so the simplest measure is that to find out the first time it hits the target, finds the target, then the search gets over at that time. So this TF, the first passage time, is a random variable. It fluctuates from one configuration to another configuration. And so you want to know what is the probability distribution of the first passage time. And then from that, you want to calculate the mean first passage time. That's the mean time it takes for the searcher to find the target. Okay? Now, let's look at what happens. First, let's look at what happens when there is no resetting. So if there is no resetting, then this is a classical problem, and you can actually solve the first passage probability exactly. And this is the exact expression for all TF. So TF is a random variable here for a fixed x0. And in fact, it decays for large TF as TF to the power minus 3/2. So this is a classic result which goes back to Levy and then Chandrasekhar in the physics literature, and then you can find it in the book of Feller and with Sidney Redner's book and so on. But the interesting point here is that this distribution has a fat tail, which is a power law tail, TF to the power minus 3/2. So that means that the mean, if you calculate the first moment is actually infinite. Okay, so this means this is a paradoxical situation. That means it definitely finds the target at some time, but the mean, the average time to find the target is actually infinite because it has a power law tail, this probability distribution of the first passage time. Okay, and physically, what this means is that there are trajectories which where the particle goes in the opposite direction of the target, and these trajectories have a finite weight. They contribute finitely to the mean, and they have the sort of non-zero probability, and they actually contribute to the mean. So if it goes in the opposite side, it'll never find the target, and they contribute to the mean, making the mean first passage time infinite. Okay, and so what resetting does when we introduce now switch on the resetting, it cuts off those wandering trajectories, those bad guys. It cuts off those trajectories, and therefore the target can be found more easily because you are getting rid of the bad trajectories. Okay, so now we want to calculate this mean first passage time or first passage time distribution in the presence of resetting. So once in a while you do reset, you come back to the initial position. And so here it's not completely obvious that it will do so, because if you go on the left, if you have a good trajectory, you are resetting it back to x0 also. So you are not letting it reach the target, but you're also cutting off the bad trajectories. So there is a trade-off between these two. And when you calculate the mean first passage time, I'll not show you the calculation. It's just again the sort of renewal calculation, quite not so difficult to do that. But when you compute the mean first passage time, so the first thing you find that the mean first passage time is finite as opposed to infinity when r is 0. So it's a finite number. That's the first effect, and it's given by a very simple formula which depends on the resetting rate r. Okay? And so the mean capture time. So if you put r goes to 0 limit here, you see that this guy diverges. But for finite r, it's actually finite. So that means resetting already improves the mean search time. Okay, so that's the main conclusion from this work. And moreover, if you actually plot this mean first passage time as a function of this resetting rate r, this curve, this formula here, it diverges at r goes to 0, that we already mentioned, but it also diverges when r goes to infinity. And this is because, if you look at the two competing limits, when r goes to 0, as I said, it cuts off the bad trajectories. So, I mean, there are these trajectories which take it to infinity when r goes to 0. That's why it diverges here. On the other hand, if r is very large, that means you are, always resetting to this initial position x0. So this is like the Geno's paradox in, in quantum mechanics, unitary evolution. And you actually localize the trajectories very much around the x0. And again, you miss the target. And that's why the mean first passage time diverges in the opposite limit as well. So it diverges in the two limits. And in fact, what happens, there's a single unique minimum at some r star in between, okay? And you can compute this very easily by taking the derivative of this equation. And so what it says is that there is not only that the mean first passage time is finite for finite r, there is an optimal r star which makes the mean first passage time minimum. That means if you reset with this particular r star resetting rate, then you will find the the mean first passage time the most in most optimized way. Okay, so this was the sort of main conclusion from this work, and this same conclusion actually holds in higher dimension as well. So I just talked about one dimension. So in higher dimension, if you are d bigger than 2, for instance, you have to put a small cutoff to the size of the target. Otherwise, Brownian motion will always miss the target. And again, you can say that you start at some r naught and you diffuse, and with rate r, you go back to the starting point, and you ask what is the mean first passage time to find this target. You can compute this in terms of Bessel functions and so on. But main point is that in any dimension, there is always an optimal r star that minimizes this mean first passage time in all dimensions. Okay, so this was these two, to summarize, there are three important facts that we learned from this simple toy model of diffusion plus stochastic resetting. There is a non-equilibrium stationary state which emerges, and there's an unusual temporal relaxation to this stationary state, which is accompanied by a dynamical phase transition. And then third thing is that the existence of an optimal resetting rate r star, which makes the diffusive search process efficient. Okay, so these were the sort of main lesson from this toy model. And then because of this, I mean, then there was a huge sort of literature which developed in the last decade or so in many different areas, which I'm not going to talk about because of time constraint, as a very long list. And this essentially this fact of optimal resetting rate and the stationary state, these two main paradigms, which are found in many different systems, including classical and quantum dynamics. So we wrote some review recently with Martin Evans and Gregory Scher, and there's also another review by Rubén and collaborators. And there are many other things which happened after that, the experiments developed and so on. So these reviews it's a very rapidly developing field, so it doesn't cover everything yet. So let me now just talk about the experiments. So far I was just talking about the model and the theory. So what about experiments? Okay. So in fact, I mean, there are two different groups which did the recent experiments using optical traps setup. So one from the group of Yael Roitman from Tel Aviv University, which I mentioned already. And the second is from the group of Sergio Siliberto at ENS Lyon. And I was involved with them, so I'll talk about their setup essentially. So this is just an optical. So one of the main problem with this, with this experimental setup was that how do you actually do the resetting, okay, of the particle? I mean, you can think of in simulations or theory, you can grab the particle and put it back to x0, but this instantaneous resetting. But how do you do it in the real experimental setup? So the idea was the following. So very simple setup. So what you do is you have a harmonic trap, for example, from the optical tweezer. And so what you do is in the beginning, trap is switched off. So you have a single particle and it's just doing diffusion. And then at some random time, exponentially distributed, you switch on the trap. And when you switch on this trap, the particle, it just moves in this harmonic trap. It's like a one-step process, and it sort of thermalizes inside this trap. So it doesn't go into a instantaneous initial position, which will be like a delta function distribution, but it actually resets to a distribution, not just a particular point. Okay, it's a thermal Gaussian distribution. And during that thermalization process, which is shown by this red band here, you do not make any measurement. You let it. So this is like the mimics the instantaneous resetting. And you can actually do this resetting pretty fast these days using what is called the engineered swift equilibration technique, or ESE technique. And so you reset the particle to a distribution, Gaussian distribution centered around x naught. And then again you switch off the trap and let the particle diffuse. And again, after some random time, you switch on the trap and so on. Okay? And then you measure the position distribution or the target, first passage time and so on. Okay? And these two steps alternate. These two steps alternate. And as I mentioned that, in this setup, you cannot really reset to x naught equal to 0, as in the theory, but you reset to a distribution which is which has a thermal distribution, which is a Gaussian distribution with width, which is proportional to the temperature, and this is the stiffness of the trap essentially. So by tuning the temperature and stiffness, you can actually tune this sigma squared. So this sigma is a new length scale that appears in the problem, which was not in the theory to start with. And it turns out, and this came from experiments, and this finite width sigma has a sort of very interesting new effects on this mean first passage time t bar to a target which is located at distance L from the initial point x naught. So I'll just very briefly mention what is the effect of this sigma. So recall that sigma is the width of the trap. So when sigma is 0, so that's the usual theoretical model basically. And so now we have a new length scale sigma. So that means a new parameter, which is the dimensionless parameter, which is the L. L is the distance to the target divided by this sigma. I call it dimensionless parameter B. So when sigma is 0, that is B is infinity, then you have this curve which is, it diverges at, so this is like a resetting rate R if you like. So it diverges here at this end and it diverges to the other end. So this was the curve when this B is infinite, that sigma is 0. And now, you can reduce the B from infinite by changing this sigma. So what you find is that for finite sigma, there's a second maximum appears. So I'm plotting mean first passage time as a function of the resetting rate R. So second maximum appears, and then it becomes minimum when R goes to infinity. And then at some point, some critical value of BC, this second maximum disappears, and you have a monotonically decreasing curve here. So this means that, essentially, so there is a sort of local metastable minimum, if you like, but there's another minimum which appears at R equal to infinity. And this is sort of easy to understand because, when you have a finite width, you can just find the target just by resetting itself. Okay, you don't have to do additional diffusion. And that's the reason there's another minimum appears. And there's a kind of spinoidal phase transition at this critical value BC, where both the first and second derivative vanishes. And then after that, R star equal to infinity is the only limit. And this is actually turns out to be quite generic in many of these experiments. That's the spinoidal transition. So this is the resetting rate. I mean, C is some just proportional to the resetting rate R. Okay. All right. So this is the thing. So now in the next half an hour or so, I want to look at the generalization of this problem to many body systems. So far I was talking about a single particle system, and so how do we generalize to many body systems? So the generalization is actually very automatic, almost it's natural. So just to remind you, what is stochastic resetting? So in a nutshell, what we are saying is that you have any process which could be deterministic, which could be stochastic, which could be classical, which could be quantum, whatever it is. It has its own natural dynamics, and you interrupt this natural dynamics at some random time. Okay, and these random times are distributed by some distribution P of tau. And then in between these interruptions, it evolves by its natural dynamics, and then again it gets reset to its initial configuration, and then it evolves again, and so on. So this is a very sort of you can apply to almost any process, your favorite process that you can think of. So it's a very, very natural dynamics. So you can think of this as a many body system also. I mean, not just a single particle problem. Okay, and Poissonian resetting is a simple case when this is exponentially distributed with some parameter R. Okay? So therefore, it's sort of very easily you can generalize to many body systems. So just to give you some example, so think of any many body system. So some examples that I have in mind is, for example, you can think of the fluctuating interface in 1+1 dimension, where your relevant degree of freedom is the height of the interface. For example, it could be Edwards-Wilkinson's or Kazar-Parisi-Chang equation. Or you can think of Ising model with evolving under the global dynamics at some temperature. And so in these systems, so essentially so there is a configuration C, which is characterized by the degrees of freedom. And these degrees of freedom in the case of interfaces is the height at different points in your system. Okay. And in the case of Ising model, these are the spins at different sites of your lattice, if you like. So it has its own dynamics. So which is, as I said, either the Ising model, think of it a global dynamics or metropolis dynamics or whatever you want. And fluctuating interfaces, it can be KPZ or Edwards-Wilkinson's dynamics. And then you evolve again up to a certain random time, and then you reset to its initial configuration, the whole system. When you reset the whole all the full configuration basically to its initial point. You can do partial resetting, but I'll not talk about that today. So let's say full configuration will reset to the initial state with some rate R. And then we ask, if we keep doing this, what happens at long times? What kind of stationary state does the system reach? Okay. So that means here I have PR of CT, probability to be in the configuration C at time t, in the presence of resetting rate R. Okay. And again, you can write down exactly the same renewal equation that I wrote down for a single particle. Namely, so you can think of this evolution. So there are two terms here. So first term corresponds to no resetting, which happens with probability to the power minus RT. This is the Poissonian resetting. And then you just have the free evolution during that period, okay? So this is just P0 of CTs. The P0 means natural dynamics without the resetting. And then if you have one or more resettings, then again, you locate the time since the last resetting, which is this tau. And during this tau, you have free evolution. And then probability that this is the last resetting is just this object here, and you have to integrate from 0 to t. So it's exactly same idea essentially as for a single particle. And you realize that you can apply to many body systems. And in particular, in the long time limit, this term you can drop out. You can neglect this term, and it goes to 0 to infinity into this integral. So it's just a Laplace transform of the natural dynamics of your problem, with the R being the Laplace parameter, if you like. Okay. So this is the non-equilibrium stationary state that your many body system reaches. And you can actually think of this again, if you are thinking of quantum mechanics, your evolution would be not just a classical mechanism, but it will be unitary evolution. And then you just, interrupt this unitary evolution by, for example, by just measuring some spin or something, which projects. So measurement basically projects the system into some subspace of the system. And then again, you evolve by unitary evolution, and again, do a measurement and so on. So you can think of many interesting protocols for devising this evolution of your system. And it's sort of very general actually. So this is the, I'm talking for the moment as the classical system. So you see that this is the non-equilibrium stationary state, and you can ask what happens in this stationary state, the properties of the system, okay? So of course, in order to characterize this stationary state, you actually need to know the free evolution at all time tau, not just at large time tau, okay? I mean, so therefore, you need to know the dynamics without resetting for all time tau, which is usually very hard because, for many body systems, we do not know what is the exact time dependence of the evolution of the probability of the configuration. So it makes it very hard. And but some problems, some progress have been made for few systems like fluctuating interfaces, then symmetric exclusion processes, and Ising model also under some approximations. And then this last one, which is this n-independent Brownian motions. And so I'll talk about that in the rest of the talk. And in fact, this is a joint work with Hernan Laralde that he talked about yesterday a little bit. So you'll see that this is a very nice physical example of the the mechanism of conditional IID variables that he was talking about yesterday. And so here it comes very naturally in a physical way. And so let me focus on the rest of the talk on this particular system here. Okay. So So let us go back to the experiment that I talked about, the experiment from the group of Siliberto. So there you had one particle only, but you can actually think of your system with many particles. Of course, these particles are in a fluid, so they have long-range hydrodynamic interactions. But for the moment, let's imagine that you switch off the interaction and they're just independent particles, independent Brownian motions, free diffusion. So then, you start, you let them diffuse up to a random time, and then you switch on your optical trap. And this is the same trap for all of them. And during this trap, nothing happens. So this mimics the instantaneous resetting. So you simultaneously reset all the particles to the origin. And then again, you let them evolve. And they evolve independently. They can cross each other, whatever you want. And again, at random time, you switch on the trap. And that means that is equivalent to simultaneous resetting of all these particles. And again, you evolve, and these steps 1 and 2 alternate. Okay? And then you ask, what happens in the long-term limit? Okay? So the point is that here, the particles are totally, non-interacting. So the simple model is as follows. So we have n Brownian motions, which are independent. They start at the origin, and they evolve freely. And after some random time, you reset them simultaneously. This is just because you reset these traps simultaneously. They are all in the same trap. They all go back to the origin, and again they evolve freely. And again, after some random time, you go back to the origin, and so on. Okay. So this simultaneous resetting actually makes them correlated in time. So between two resettings, they are totally uncorrelated. But because they are all in the same trap, and you are simultaneously resetting them, so this creates a dynamical correlation between the particles. So it's like, imagine that in this room, we are all independent. We don't know each other, and then we go outside. But when there's a bell which rings, all of us are carrying a bell, and when the bell rings, you all have to come back to this room. Okay, and this fact of coming back to this room together, that makes us correlated essentially. Okay, so it's a non-trivial correlation which is generated by the dynamics itself. And it's also similar to what Chandan was talking about yesterday in his active particle systems. So essentially the active forces, they are all uncorrelated, but when you switch on the dynamics, is the dynamics of the sort of medium which makes them correlated, even though they are uncorrelated to start with. So this is a sort of very simple mechanism of generating correlations. So to prove this, so you look at the joint distribution, the joint position distribution of all the particles, x1, x2, x3, xn. And again, it approaches a non-equilibrium stationary state. And as you saw there, so this is the Bayer propagator. So Bayer propagator means since the last resetting, so they are evolving independently. So this is just a Gaussian with tau. Tau is the last time since the last resetting. But this tau itself is random variable. It's distributed exponentially with rate r. Okay. So you have to, so as I said, this is the stationary state from the general formula that I showed you before. This is the general formula. So here is just P0 of C tau is the free evolution of the system, and in this case they are just independent Brownian motion. So it's just a product of the Gaussian propagators basically. Okay, and you just have to multiply by. So here you see that this random variable tau. I mean, we are not putting in by hand, but here it's automatically coming from the dynamics of the system itself. And this is exactly has the structure of this conditional IID distribution. That means inside the integral there is a factorization because they are uncorrelated, but because they share the same parameter, same random parameter tau, they actually get correlated. So after you do the integral, it's no longer factorizable. Okay, and so this is the sort of mechanism behind this the conditional IID structure that Hanan was talking about yesterday. And so as I said, the simultaneous resetting is the sort of mechanism that generates the interactions between the particles. Okay. So in fact, you can think of this as a gas of particles. So in the stationary state, you have a joint distribution of these particles, and this gas is strongly correlated because and basically everybody is attractive all-to-all interactions, all the particles, because they all are simultaneously reset. You can actually easily compute the correlation function. Here I look at this square because by symmetry, if you just look at xi xj average, the connected part of it is 0 by symmetry of the xi square. So you have to go one step beyond. You look at the xi square, xj square correlator, the connected part, and you can check easily that this is just a constant, which means that they're all positively correlated. There's an effective attraction between the particles. Attraction because the trap makes them come together as time evolves. And so you have a gas of particles, which is strongly correlated gas. And then, but this is what is nice here is that inside the integral, they are independent. Okay. So it actually makes it solvable. That means if you want to calculate any observable, okay. So for instance, you can calculate many other different observables. So for example, you can ask, what is this? So I have a gas of particles in the steady state, and what is the average density of particles? Or what is the distribution of the kth maximum? This is the order statistics that Hernan was talking about. You can ask what's the distribution of the rightmost particle, or what's the distribution between the spacing between successive particles, or full counting statistics, which means if I take an interval from minus L to plus L, so the number of particles in that interval in this gas is a random variable, and I can ask what is the distribution of this random variable. And these observables are sort of very natural in random matrix theory that Jack talked about yesterday. If you have a, the random matrix problem, so there you have the eigenvalue. So there you have a gas of eigenvalues in one dimension. And so these are the observables that people typically look at. That means average density, for example, in the case of the GUE or GOE random matrices is given by the Wigner's semicircular law, and then the gap distribution is given by the more complicated object. Spacing distribution is Wigner distribution, and full counting statistics is also known. So these observables have been calculated in random matrix theory for a very long time, and that also represents a strongly correlated gas of particles. But here we have another system where, again, you have a strongly correlated gas of particles. So these are the natural observables to look at. I have a slight different background in random matrix theory, so for me it was very natural to to study these observables. And in fact, they're all very non-trivial, even though the actual structure is very simple. So the point is that you calculate any of these observables for the ideal gas. This is like an ideal gas with no interaction, and then you just have to integrate over this parameter. So I'll not go into the details, just to show you some results. So for example, if I look at the distribution of the rightmost particle in this gas, so this is the maximum of x1, x2, xj, xn. So the long, for large n limit, it approaches a scaling form. So ln here is scale is square root of log n. Okay, so that's a scale. So the typical size of this, so if you look at your gas here, okay, I don't have this. Yeah. So you have a gas of particles, and the rightmost particle, typically it scales like square root of log n. And if you scale the position distribution of the rightmost particle by the scale, so this turns out to be a distribution, which is very simple function, 2z e to the power minus z square. So it goes to 0 as z goes to 0, and it vanishes as a Gaussian for large z. So this, in the random matrix context, this will be the famous Tracy-Widom distribution, if you like. And here we have a different distribution. Similarly, you can calculate the gap distribution, and gap distribution is highly non-trivial. Again, there's a scaling. Typical gap size goes like 1 over square root of log n in the large n limit. And the gap distribution has this scaling function, which has a non-trivial stretched exponential tail. Which is exponential minus z to the power 2/3. And here you notice that this gap doesn't go to 0 here, gap distribution. So there's a finite probability that the gap is 0. That means the particles can be very close to each other, because this is an attractive gas, as opposed to eigenvalues of a random matrix where they repel each other. So there the gap distribution actually goes to 0 as the argument goes to 0, but here it goes to a finite constant for a small argument. So you can calculate all the other observables. I will not go into the details. And let me just tell you briefly two other different experimental protocols where similar mechanism appears. So the first one is you now take these n particles and you have a trap, and you change the frequency, the stiffness of the trap. So from mu1 x squared by 2 harmonic trap with mu1 as the stiffness. So you change from mu1 to mu2 with rate r1 to r2. So you keep doing this, close and opening and closing of this gap. So the previous example is when mu2 was 0 essentially, but you can do it from mu1 and mu2. And you can ask again, what is the, the distribution of the joint distribution of the particles in the stationary state? Or a second protocol is again in the same system. You take n particles, you have this harmonic trap, and you take the trap center and you just, put some stochastic motion to the trap center. And because they all are in the same trap, so they again get correlated, these particles. Okay, so these are the two protocols. So with the first protocol, the frequencies, the stiffness changes with rate R1 and R2. And again, you reach a correlatedness, and you can calculate all these observables in this correlatedness because they all have this, this CIID structure, conditional independent IID structure. And similarly here, where I drive the trap center by some stochastic process, and again, you can show that it reaches a correlated non-equilibrium stationary state. This is a joint work with Sanjib here, and again, you find that there's a non-trivial behavior of all the observables, and all these non-trivial observable properties, they emerge from this CIID structure, which Hanan talked about yesterday, which means that the joint distribution in the stationary state you can write as a product inside the integral, the product of individual particles. So it's like an ideal gas, but they share a common parameter, and this parameter itself is random, distributed via h of u, some h of u. And we have seen this example where it appears very naturally in this experimental setup of optical traps. Okay, so again, you can calculate all these observables for both protocols, and they are very sort of non-trivial behavior, which are in these recent papers here. Okay, so let me now just conclude. So summary and conclusion. So I, basically what I gave you is a brief and partial overview of stochastic resetting, and as you saw, this is a very rapidly evolving field of research. So the main, sorry. Right. So the main thing is that, okay, so there is this new non-equilibrium stationary state. Then the second point was that there's an unusual temporal relaxation to this stationary state, which is accompanied by a second-order dynamical phase transition. And the third thing is that the existence of an optimal resetting rate that makes the search process efficient. So these are the three things that we learned from a very simple toy model of diffusing single particle with stochastic resetting. And there's new experiments which led to new interesting questions. For example, this spinoidal phase transition here. And then I showed you how to generalize it to many body system. I did not have time to talk about the quantum evolution. There are a lot of work which is being done for quantum systems as well. And what we see is that the simultaneous resetting is a very sort of practical way of generating non-trivial correlations through the structure of conditional IID variables. And there there are many other sort of recent directions in which people are working on these stochastic resetting problems. So one thing is, I just go through briefly. I mean, so the geometrical properties of, for example, territory covered by a resetting Brownian motion, you can ask, how much area does it cover, the span of the convex hull, number of distinct sites visited, etc., etc. So that's sort of one direction. Then people are starting with resetting with memory. Denny Boyer and collaborators, they basically studied this model where you reset to a site, not always to the origin, but to a site which has been visited previously with some probability. And so they lead to very interesting anomalous diffusion and so on. Then you can study resetting Brownian motion with constraints. So for example, you can have resetting Brownian bridge, where you are constrained to go back to some initial point, like the animals do. After searching food, they always go back to their nest and so on. So, and then there's also the first passage resetting. That means you reset not at random times, but you reset only when your system, when your value of the position of the particle exceeds some level. Like for example, in a electric network, when the voltage exceeds some critical value, then you reset to its zero value. So there's a load dropout. So this was the sort of area which was started by Sidney Redner and collaborators. And Then there's the optimal control theory, which is sort of very recent area in which there are a lot of work which is being now done, mostly by Francisco Mori and also Luke Mahadevan from Harvard. So they are doing a lot of nice experiments on this. And then the cost of resetting. So this is something that we are working on right now with my collaborators from Edinburgh and other people, and also from Stockholm group. I mean, there's a cost of resetting. So here I just talked about mean first passage time, but you can think of that when you reset, there's a cost involved, and there's a lot of work there. And so as I briefly alluded to, resetting in many body classical systems, but there's also work on quite a lot of work on resetting in quantum many body systems. And here, as I said, you can evolve this quantum system state by unitary evolution and then interrupt it by measurement or some other projection operator, and then again evolve and so on. And again, you reach a non-trivial stationary state where you have non-trivial entanglements and other quantities induced by resetting. And so there's a lot of many other directions which are being pursued right now. So the take-home message is that stochastic resetting is a very rich and interesting subject with a lot of interesting static and dynamical phenomena. And so there was a just some of you might be interested. So let me just advertise. There was a special review, kind of special article in special issue in GFEZ on precisely on stochastic resetting in 2022, I think. And there's a lot of other interesting articles that you can find here in this special issue. And let me just finish by thanking my collaborators. These are my graduate students, Marco Bedoli, Ivan Buranev, Benjamin Dubruin, Constantino Di Bello, Mathis Gueno, Matthew Magini, and Francisco Mori, who is right now postdoc at Oxford. And there's a lot of collaboration here with Mexico, with Denis Boyer, Hernan, and there's collaborators and students, Sergio Siliberto's group in ENS Lyon, and many other people here, Sanjib, who is present here. And so I was really fortunate to collaborate with many people here, and that was a really nice experience. So thank you very much for your attention. Yeah.
Okay, thank you, Satya. Any questions?
I want to ask, when you apply this to quantum systems,
yes,
can you formulate that in terms of a Lindblad evolution?
Yeah. So if you want to introduce dissipation, so these are so far, as far as I know, there's been only one work including Lindblad dissipation, but they're essentially exactly similar things. So it's unitary evolution for a random time, and then when you measure, then measurement is also it's like interacting with a heat bath or something, and so that you can introduce the different the Lindblad operator there, how the density metrics change, and then again it evolves unitarily and so on. But it's not been explored that much. No, it is in some sense quantum trajectories, except that what we're looking at here is that the density metrics, if you first of all, you are making this measurement at random times, not at stroboscopically at periodic times. And if you make this at random times, then in long time, the density metrics become time independent. And that's the sort of this non-trivial stationary state I'm alluding to, basically. Okay.
Maybe there was one question here and then.
I have two questions.
Yeah.
The first one is it possible to incorporate interactions in the resetting of many particle systems? And the second is, are there any experiments on these many particle systems?
Okay, so to start with, let me answer the second question first. So far as I know, there is no experiment on the many particle system. So I've been talking to Sergio, trying to convince him to do the experiments with many particles, okay? But it has not been done yet, okay? Now, coming back to your first question, that whether is it possible to do interacting systems, okay? So the main problem, as you see, resetting actually what it does is just generates, the correlations dynamically, okay? But in an interacting system, to calculate, you need to know some of the evolution dynamics without resetting at all times, which itself is a very difficult problem. Okay, so that's why it's not so easy. But some work has been done, for instance, for the Ising model. I mean, you can just use the global evolution, and you can ask. So, which means the following. So, I suppose you take 2D Ising model, and let's say you quench from higher temperature to low temperature below TC, okay, and you evolve the system, and then again you reset with some rate back to the initial configuration, and you can ask. So this is an interacting system, of course, okay, and you can ask the usual question that it reaches a stationary state. So what happens to the phase transition, for example, the usual second order phase transition? Does it stay there, or so? It turns out that there's a new phases which appear. I didn't talk about it here, which we call the pseudo ferromagnetic phase, where you have a gap in the spectrum, but the order parameter is still, so its order parameter is non-zero, but it's still, this spectrum is gapless basically. So some aspects of this new phase introduced by resetting is that there's some aspects which are like ferromagnetic and some aspects which are like paramagnetic. So there are some works, but not, this is a sort of wide open area. I mean, with the interacting many body systems, what they do under resetting. So only very few, as I mentioned, just Ising model and symmetric exclusion process, which have been studied, but not much basically.
Okay, thank you.
Yeah.
Yeah, thanks for the beautiful talk. So for me, this is new. Sorry,
No, sure.
Because it's not my
At least there's somebody who has not heard this talk, so that's nice.
Yeah, no, it's fantastic, and it creates a lot of associations. So one, of course, is working in light matter interaction. We always have periodic kind of driving.
Absolutely.
But couldn't this be mapped into your problem if you have an interacting, basically non-regular dynamics?
Yes.
Because then
absolutely
the non-regular dynamics would cause a stochastic.
No, this is a very good question. And in fact, I mean, what happens is that you see, this is I mean, I just did it here for exponential distribution, just for Poissonian resetting, just for simplicity. But okay, sorry about this. Yeah. So you see, what happens here is that this guy, if you do with arbitrary distribution, what happens is that you just replace this by P of tau. Okay. So again, you have a stationary state, and in case of periodic case, this is just a delta function. Okay. So then you have you can have a periodic stationary state, not really, it's a stroboscopic thing. So people have studied actually for different types of resetting dynamics. Okay, these are typically non-Markovian because it's not exponential, and but this is true. I mean, when you change this distribution, the stationary state can have very different characteristics depending on this P of tau, basically. So in the light matter interaction, in fact, I mean, what people have studied, for instance, I mean, this, what is this model called? This, when you have bosons, and I keep forgetting this, bosons interacting with this qubit, basically. So this is somebody's model, I forgot. Anyway, so these people have studied that with resetting, essentially. But and James Cummins model, yes. So thanks. Yes, exactly. So James Cummins model with resetting, people have studied and things like that. So yeah, so you can actually study for with arbitrary resetting distribution time here. I mean, so that's true.
If I may, 1 second.
Sure.
So, I mean, of course, the natural playground for this diffusion quantum mechanically is dispersive wave packets.
Yes.
And that's also a famous example, like in Rydberg wave packets,
Mm-hmm.
which you stabilize by periodic driving.
Right.
I think this is
absolutely
exactly
no. This is
setting in another way.
No. This is true. This is true. No, this is probably one way to look at these problems in that way, and it has not been, at least not to my knowledge, not in this context, it has not been explored. I mean, yeah, this is a good point. Yes.
And
agree.
a big field, I mean, this is what Jacobus just said is basically these kind of decoherence-free subspaces.
Yes.
This must be totally related. There one has Lindblad dynamics.
Exactly.
And you get a kind of stationary state in the long run under certain conditions.
Yes.
But of course, there the non-trivial part is the dynamics, right, which you make very simple in order to make it solvable, I guess.
Right.
Because if that has certain symmetries and so on, then you get interesting effects.
Yes. No, actually, I mean, okay, so there's one general thing is that, you can take any quantum system, I mean, whatever the density matrix is. So the analog of this classical thing here, for the quantum mechanics, it will be the density matrix, actually. So density matrix in the long time limit, if you, do the unitary evolution followed by some projection, basically, okay, and let it evolve, the density matrix will reach a stationary state. And this is non-trivial because, it has off-diagonal elements which are non-zero in the presence of resetting. And then you can actually ask, in this stationary density matrix, what are the different properties of this system? So this is one way of asking quantum resetting thing. The other thing is in the measurement-induced theory, basically, which means, you can ask what is the analog of first passage time in quantum systems, okay? And this is very interesting because what happens is that people actually, what they study is the first detection probability. That means, for example, you can just take a single qubit, let's say upspin or downspin, and you evolve this by some unitary evolution up to a random time. And then you make a measurement, a detection basically, and you try to, let's say, detect in the down state. So if the detection is yes, okay, then of course the system gets projected there. If it is a no, then it gets projected in the opposite space. And then again, you evolve unitarily. So you can ask, I have a no, 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 and then at some point, I get yes. So that's the first detection time. So that's the exact analog of the first passage time in classical systems. So you can ask what's the distribution of the first detection time under this resetting. And this, again, people can compute it for several models. But of course, in general, many body system, it's hard to compute. But at least for a two-level system, you can compute this easily, actually. So, and that has been done. And even, I mean, if you calculate the mean detection time as a function of this, this R, which is the interval distribution, what you find, again, there's an optimal value of R star, which makes it minimum, the first detection time, essentially. So some features seem to be, carried over to quantum mechanical system as well. So, yeah.
Yeah, I would say this is a general model for decoherence in the
Yes.
end. So Zurek would call basically the environment your
Yeah, but I mean,
probing.
but yeah, sure. Okay, sorry. Okay, so you can discuss this. Yes. Sure.
Sorry.
Hi. First of all, thank you for this beautiful talk. I remember the first time you talked about it, at least I listened in 2011 in Kolkata conference, now here.
That was really fresh at that time.
Yeah. A lot of things changed by that time.
Yes.
So I have two questions basically. The first one, that you give an example for the searching of the target, and when it resets, it take a new path.
Yes.
So it look like very much like an self-avoiding random walk with resetting. So
No, it takes a new path, but it's a stochastic path. It's not that, there's no memory induced. I mean, because in self-avoiding random walk, it does not visit the sites which it had previously visited. But here you don't do that. I mean, here it's you can visit the sites which you have previously visited, okay? But it's a completely stochastic thing, okay? So you don't put in this self-avoidance by hand. I mean, and yet it finds the target in a shorter time. So it's much simpler system than self-avoiding walk, if you like.
Okay. And the second question is that you mentioned there is a non-equilibrium stationary states and then there is a transition state. Now, following the question of Rubén, if somebody try to study the diffusion annihilation or diffusion aggregation system with resetting, so do you think that can give a crossover in the change of the concentration or anything like that?
No, it will reach a stationary state surely. I mean, it will reach a station if you do the resetting of any aggregation dynamics or whatever, and people have studied that also, reaction diffusion system. And if you do reset, you will reach a stationary state, okay, with non-trivial properties basically. So that's the whole point, that that with this very simple mechanism, you can actually generate a stationary state with a strong correlations between particles basically, okay. So there's one system I know. I mean, I think it was studied by Malte Henkel and collaborators. That was just I don't remember now exactly, but it was, I think, diffusion with ballistic annihilation or something like that. And then you put resetting, and then you look at the steady state, what happens. I mean,
Okay, we have a last question by an online participant. Gabriel, if you can switch on your microphone and make your question. please.
Hello, can you hear me?
Yes.
Okay. Well, first of all, congratulations on your talk. It was really interesting. I just have one question. For example, what is the difference? For example, if I want to measure the mean first passage time for n non-interacting particles,
No,
do I
I
get
didn't hear the question very well.
sorry?
There's a kind of echo. I couldn't hear the question very well.
For example, if you have n non-interacting particles
Yes.
undergoing Brownian diffusion,
Yes.
and you have resetting,
Yes.
so do you get the same result as, for example, having just one particle
Okay. Okay.
and
Yeah.
performing Brownian motion and measuring,
Yes.
for example, the mean first passage time?
Yeah.
Do you get the same?
Yeah, I understood. So this is a good question. Actually, you can ask, if I have n independent searchers, Brownian searchers, and I have a single target at the origin, and then you can ask, is there an optimal resetting rate R star, which is now a function of n, and how does it behave with n? And it has actually very interesting, I didn't talk about it here, it has a very interesting dependence on n. So there is an R star, okay, and as long as n is less than equal to 6, okay, then it turns out that there's a finite R star. And when n, the number of searches, is bigger than 6 for simultaneous resetting, then it turns out that you should not reset. Okay. This was for simultaneous walkers, and when the walkers are independent, this was actually Sid with I don't remember who was with your collaborator. Huh? Yeah, maybe it's Mirsan. Okay, no, I think it was Katerina Di Bacco. Yeah, probably, yeah. So anyway, so essentially, whether it's independent resetting or simultaneous resetting, both cases there is a critical value in C, which happens to be 6 in one case and 7 in the other case. So below which, you should reset, and above which you should not reset. So R star, if you like, when you plot it as a function of n, for n bigger than 6, it becomes 0. Okay. Does that answer your question?
Okay. Yes. Yeah. Thank you very much.
Thank you, Satya,
Okay.
for the nice talk, and we see each other in back in principle in. Okay, let's make it a little bit. So maybe 20-minute break instead of you,
Could you please do that? Yeah, thank you. Welcome everyone in our second session of the day. After the first morning session with a beautiful talk, we will still continue with the same similar line of the problem on resetting. In the second session, our first speaker is Sidney Redner from Santa Fe Institute. And his title of his talk is First Passage Resetting and its Application to the Optimization and Wealth Sharing.
All right, thank you very much. And thank you to the organizers for inviting me. It's been a very nice meeting so far, and I've learned a lot. And so the work I'm going to be describing to you today is in collaboration, a very pleasant collaboration with Benjamin de Bruyn, who was Satya Majumdar's PhD student, and Julian Randon-Furling. And Benjamin is a person who I have never met. So hopefully I'm going to meet him someday. So, so the outline of my talk is, first of all, the first 10 minutes are going to be really elementary. It's meant to be for people who know nothing about the field. I just want to describe what is a first passage process. And then I'll go on to describe this notion of first passage resetting, which is one of that long list of other problems that Satya mentioned at the end of his talk. And I'll then describe two applications. One is an optimization problem that's controlled by first passage resetting, and then another very simple model for the dynamics of individualism and altruism. Okay, so first of all, what is a first passage process? So the idea here is you start with a random walker initially at the origin, and so the way that if for people of a right age, if you have children who are about to finish high school and go off to the world, either to college or whatever, and so they wander around aimlessly in the space of opportunities. And a question you might ask yourself is like, will you ever see your child again? And so this issue, will the walker ever return to the origin? And when will the walker first return to the origin? These two things embody a first passage process. So in contrast to what we normally think of as where is the random walker, we want to know when the random walker will return home and ask you for more money. So let's solve the first passage problem in one dimension. And there's many ways to solve it, but certainly the slickest way and the simplest way is by the image method. So if we have a random walker that starts at x naught, we know that it will spread into a Gaussian probability distribution. But for our problem, if the random walker returns home, this is the origin here, if we return home, the process ends. And so we have to somehow impose a boundary condition that the process ends when we reach the origin, which is the same as imposing an absorbing boundary condition that the concentration here is 0, because if I reach here, the process ends and I remove everybody. And so how do we solve the diffusion equation with this boundary condition? And the slickest way of doing it is to put an anti-Gaussian at minus x naught, and you can see just by symmetry that the concentration is necessarily equal to 0 at the origin. So this summation of an initial Gaussian at x naught and an anti-Gaussian at the mirror image point solves the problem we want to solve, which is what is happening, which is that the concentration vanishes at the origin. And now what we want to compute is what is the probability that some random walker reaches the origin for the first time from this probability distribution. And so first of all, the probability distribution is a sum of a Gaussian and an anti-Gaussian, so blue and red for the negative part, centered at x naught and minus x naught. And what we want to calculate then is the first passage probability. And because we start with a normalized initial condition, we start with like a delta function at x naught, the first passage probability is exactly the same as the diffusive flux to the origin. And the diffusive flux is just the gradient of the concentration field. And so if you take this concentration, do this calculation, you get this first passage distribution. And it took me 20 years before I learned that this is also called the Levy-Smirnov distribution, and sometimes called the inverse Gaussian distribution. And this is one thing that always drove me crazy when I was entering this field, is that the nomenclature is so different depending on the communities. And so it's only recently that I learned that this is also called the Levy-Smirnov distribution. Anyway, So here is a plot of our first passage probability on a double logarithmic plot. And so you see that for very short times, it takes finite time when your kid is already off in college, it'll take some time for your kid to come home. So the time to reach the origin, the probability of reaching the origin really quickly is actually very small. It rises to a maximum, and then there's this very long time tail. This is a power law on a double logarithmic plot with a slope minus 3/2, which reflects the t to the minus 3/2 down here. And so let me just outline some basic consequences of this first passage probability, because they're very simple and very profound. And if you haven't seen them before, it's really quite amazing. So the first one is what I call the hitting probability. You start at some point x0 now, and I ask, what is the probability that it will eventually come and reach the origin? And so what I have to do is integrate the first passage probability over all time. And when you do that, you find 1. So if you're worried that when you send off your kid to college in a one-dimensional world of opportunities, you will see your kid again, guaranteed. If you wait infinitely often, your kid will come home. But the time that it takes for your kid to come home is infinite. And it's infinite because there's a t to the minus 3/2 tail down here. And so in the long time limit, you can forget about the exponential. You're integrating t to the minus 3/2 times t dt, which diverges at the upper limit. And so the time is infinite. So the point here is that even though you're sure to return, the time is infinite, which that dichotomy is what makes first passage so interesting even after 120 years of study. But the typical time turns out to be finite. So the thing is that you see here that this first passage probability, there's a big peak sitting here. And so typically you'll leave your system at around this time variable. And so there's a typical time which is finite. In fact, it's not, well, okay, it's less than infinity and it's very finite. But when I say the word typical, like that kind of sounds wishy-washy. So let me try and give you a precise way of defining a typical time. And a natural way of doing that is by computing the concentration, the integral of the concentration for some typical position to infinity. When half the concentration is outside of x typical, that means that you've defined a typical value, because half the concentration is outside x typical, half the concentration is inside of x typical, and so that gives us a precise meaning of what x typical means. And so if you compute this integral, so this is what it looks like, a bunch of error functions, and you have to set this equal to, setting this integral equal to 1, it turns out to be this thing. This is now a transcendental equation, which you can't solve analytically, but you can certainly solve numerically. And this is what comes out, that the typical position of your random walker, even though the average position is diverging, the typical position is getting drawn towards the origin and hits the origin at a time. And so this time here is relative to the diffusion time, x0 squared over d, and this typical hitting time is 1.1 diffusion times. So what we find then is, a typical return. I mean, a typical time which is finite. Last major consequence is that the returns are frequent, namely the number of times that I will return to my daddy's home and ask for money in a time t will go like the square root of t. So I return pretty often. And a simple way to see that is that if you have a Gaussian probability distribution who has a range root t, then in a time t, I've taken t steps. And so that means that at each one of these points, I'll typically visit each one of these points of the order of square root of t times. And that means that in particular, I'll visit the origin root t times. So the thing about first passage in one dimension is that there's this fundamental dichotomy. You're sure to return, the time it takes is infinite, the typical time is finite, and there's lots of returns in a time t. So I now want to, with that brief introduction out of the way, I want to turn to resetting processes. And so we've heard a very beautiful talk from Satya just now about fixed rate resetting. And so in fixed rate resetting, in a space-time picture, we have a random walker that starts at the origin. And so here in a space-time plot, so time going to the right, space going up, a random walker does a trajectory, and at some random time, you reset it back to the origin. Again, reset back to the origin, reset back to the origin, reset back to the origin. And the crucial point here is that the time between typical resets is 1 over the resetting rate. And the crucial fact here is that this resetting time is finite. So now let me turn to first passage resetting. And first question is like, why would you even care about first passage resetting? And a very important motivating factor is what happens inside the brain. We're full of 10 to the 10th neurons. They're all subject to fluctuating voltage levels. These neurons will integrate the voltage that they feel, and they will fire at some rate. And then they send a signal to some neighboring neurons. And basically, that's how we think, is by these neurons firing all the time and sending signals to neighboring neurons that then will fire. And so this integrate and fire neuron model was first actually presented by Gerstein and Mandelbrot in 1964. So that's really the motivating factor for thinking about first passage resetting. And so more recently, there was some work by Martin Evans, who is Satya's collaborator. And then this is our work on the subject. But let's just make a little picture to really hit home the difference between first passage resetting and constant rate resetting. So in first passage resetting, we imagine that there is some threshold level, the threshold level of an integrate and fire neuron, for example, and we have a stochastic process that when it hits this level, you reset it. And you wait until it hits that level again and you reset it, and so on. When you only hit that level and reset it. So it depends on the random walker getting to this specific level rather than like how long it's been going. And the crucial point here is that the characteristic time between resets is the first passage time. And as we've seen, this average first passage time is infinite. And because the average first passage time is infinite, this is a non-stationary process compared to the stationary process that happened at constant rate resetting. So let's just review. I mean, Satya already did a great review of it, but let me say the two main points about constant rate resetting is that you go to a steady state and that it renders a search time finite in a geometry in which the search time is typically infinite. And what we're going to see in first passage resetting is, first of all, there is no steady state. And so because there's no steady state, it now becomes an interesting exercise to ask, what is the probability distribution of a random walker that's moving according to first passage resetting? And as I'm going to show, there's a very nice geometric path decomposition to actually compute this probability distribution exactly. So let me now show you with very little, with only pictures, how you can calculate the probability distribution of a diffusing particle in first passage resetting. So let's think about, first of all, again, space-time picture, time going to the right, space going this way. We have a diffusing particle or a random walker that when it reaches L, it gets reset back to the origin. Reaches L, gets back reset to the origin, and then gets reset to the origin. And I want to ask, what is the, for example, here I'm asking for the third time that it reaches position L, the third passage probability. What is the third passage probability in the presence of resetting? And in general, we can think about nth passage probability. And so here comes a slick trick, which is this. All I do is I just translate the second interval by distance L, the third interval by distance 2L, and what you now have is a Brownian motion that reaches 3L without any resetting. So there is exact one-to-one mapping between the nth passage probability to position L with resetting to a first passage probability to NL, or 3L in this particular case, without resetting. And we can exploit this very simple fact to actually derive some cool things. So now I want to calculate the probability distribution of a random walker that starts at the origin and ends up at this point here, X. I want to ask, what is its probability distribution? And as you're going to see, it turns out there's two different answers depending on we're interested in X positive. Here, X is a little bit above, so it's positive X or negative X. Turns out that positive X is a lot harder than negative X, and it's interesting that these two different cases are actually very different. So what I want to compute then is the probability that I find X, and by definition, because of resetting, it has to lie in the range between 0 and L, because if it's above L, it's going to get reset back to 0. So it only can lie inside of this regime, and we have, in this particular case, we have 1, 2, 3 resets. So the probability that X is in the range 0 to L in the presence of 3 resets in this cartoon, but n resets in general. And so what I'm going to do is the same kind of geometric decomposition as before. which is just this. I just take the second segment, translate it by 1L, the next one by 2L, and the last one by 3L. And so now you see that this looks like just a unrestricted Brownian motion, but we can't go above 4L, because if we went above 4L, that meant that this last segment would have had to have been reset. So it turns out then that the probability distribution to be at position X in this range 0 to L is the same as to be in the range 3L to 4L in this specific example with no resets at all. And so there's actually another restriction here, which is that the maximum of the random walker can't be above 4L, because if the maximum was above 4L, a reset would have had to occur. So there's a one-to-one mapping between the probability distribution that we want to calculate and the probability distribution of a non-resetting random walk that lies between NL and N plus NL with no resets. And so to calculate this probability distribution, we can take advantage of a very beautiful formula by Levy in 1948. And what he was able to compute in a very nice closed form is the probability that a random walker that starts at the origin is at position X, whose maximum M is by definition is bigger than X at time t. So there's a very beautiful closed form solution by Mr. Levy. And so we can use that to then compute our probability distribution to be at position X at time t. So we saw that from the previous slide, we had to have it's the same as being at position X plus NL, where N is the number of resets, and the maximum has to be bigger than 4L in the previous slide, but N plus 1L, and no resets. And the number of resets is an arbitrary variable that can happen as many times as you want. So we have to sum up over all possible number of resets. And because of Levy's formula, we can just do the calculation straightforwardly, and out comes not that nice necessarily, because it's an infinite sum, but it's a closed form solution for the probability distribution to be at X positive. Let's now do X negative. And it's kind of cool that the two cases are so different from each other. And in this particular case, it turns out we can just basically do a little bit of sleight of hand. As you're going to see, I'm going to do nothing except just change around some of the segments of this random walker, and the answer will just pop out with no work. So let's think about a random walker that starts at the origin, and there's the resetting point at L, and we want to know its probability distribution for X negative. So we start at the origin, here's the final point X, it's anywhere lower than 0, so it could be anywhere from 0 to minus infinity. And so here's a typical trajectory that has 3 resets before it reaches its final point, 0. And if it turns out that the number of resets is odd, I'm going to do the following trick. I'm going to take the odd numbered resetting segments before each odd number resetting. I'm going to take the segments and just translate them by L and invert. So watch what happens. I'm going to just translate those segments. I haven't changed the probability of anything because it's a one-to-one mapping. And then I flip them, which also is still a one-to-one mapping. And what we have here is a random walker that starts at L and ends up at X with no constraints at all. And so we have free diffusion from L to X. On the other hand, if there's an even number of resets, we take the even number segments and we translate them by L and then flip them over, one-to-one mapping with everything. And so we now have a path that goes from 0 to X, again, with no constraints. And so the sum of these two things will give me the full probability distribution for X less than 0. So there's the answer. Very simple and very cool and highly non-trivial. If you want to do it the hard way, you can do it the hard way by writing the renewal equation, as you saw in Satya's talk, and going through a whole bunch of calculation. And at the end of the day, you'll get the same result. Okay, so I want to now talk about 2 applications of this first passage resetting. And the first one is to a very simple optimization problem. And so here is, since I'm a theoretical physicist, this to me is a machine. A line has a single operating coordinate. And I want to understand how to optimize the performance of my theoretical physics machine using first passage resetting. So the idea here is the following, is that I have this machine, and you can think of this as this thing is a measure of the performance, the operating coordinate of my machine. So if I'm driving it at L, that's like sort of redlining on a tachometer of a high, of a sports car. I'm just driving it like 140 miles an hour. And the problem is that, well, if it's really thrilling to drive a car at 140 miles an hour, but the chance that it's going to break down pretty soon is pretty high. And so what happens is that as you try and press on the accelerator and increase the performance of the car and go 140 miles an hour, all of a sudden, like a cylinder will explode or something like that. You have a breakdown. You got to take the car to the shop and start all over again. And so this is the process that I want to try and understand how to optimize the performance of this type of a one-dimensional machine, a single coordinate machine. And so we have to define some kind of a measure that quantifies the optimization of this process. And so what I'm going to define as my objective function is something which is, you get a positive contribution if you're driving your car at 140 miles an hour and everything is cool and copacetic. Well, that's great. And so when your coordinate is very close to L, and for the time that you're doing it, you get a positive contribution. So when X is very large, close to L, and you sum up over the time that you're driving this, you get a positive contribution to the objective function. But if your car breaks down, then there'll be a cost for the breakdown, because you got to call the tow truck, you got to take the car back to the shop, and then you got to pay your bill to fix the car. So for each breakdown, there is a cost C and the number of breakdowns over a time T. So if I do this over a long period of time and divide by the total time and take the limit as time goes to infinity, this will give me a time-independent measure of the thing that I want to try and maximize in this process. So this is the problem that I'd like to analyze. So here's our objective function. And one more thing that we need in order to have a well-defined or a well-posed problem is we've got to define a protocol, like how are we going to drive our car? And so before I knew what the term was, I used to call it the floor protocol, which is that as soon as you got the car to the shop, you press the accelerator down to pedal to the metal to get it going very fast again. And so it turns out that in optimization theory, people call this the bang-bang control mechanism. So what we want to do here is we want to optimize this objective function with this protocol that when I get behind the wheel of the car, that I'm tempted to floor it. And let's see what happens. So in order to make this mathematical, what I want to do is I want to first solve the position of that one-dimensional performance coordinate on this interval 0 to L. And so what I'm going to be solving then is the convection diffusion equation, because what I'm imagining then is that there's some stochasticity, because when I press down the accelerator, I don't press, there might be a stop sign somewhere, I got to let up, or there might be a hill somewhere, or cars in front of me. So I'm trying to always go as fast as I can given constraints. And so the way that I try and implement this is by saying that the coordinate is undergoing convection plus diffusion. So this is the convection diffusion equation. And then the point is that if I reach x equals L, this is the flux going out at x equals L, and then return to x equals 0. So that's the corresponds to the breakdown. And we have to solve this equation subject to some boundary conditions that when I reach L, there's no concentration because the system's broken down. I'm computing the flux at the right edge, and that's equal to there's a typo here. This should be x equals L. The flux at the right edge is what's being input to the left edge of the system. So it's a kind of a standard problem to solve, and so we solve it with some algebra, and so here's the answer for the steady state concentration. So this is the position of your accelerator in the steady state. And here there's sort of dimensionless numbers that characterize the relative role of convection versus diffusion. The Peclet number VL/2D is the natural measure of the ratio of stochasticity to the urge to floor the accelerator of your car. The second thing we have to do to solve this problem, so that solves the first half of this. The second half is this part, which is how many resettings will occur. And so to find the number of resettings, we have to compute the first passage probability out the right edge of our interval. And so that's the diffusive flux, that's the flux, which has a diffusive contribution and a convective contribution. And again, there's a bunch of standard calculation that, you know, is standard in this whole game of first passage processes. So I won't spend any time like saying anything more about the calculation, except to say you can do it. And then to compute the number of breakdowns, we have to write a renewal equation, the same type of renewal equation that Satya mentioned in his talk, which is that the number of breakdowns at time t, well, that's 1 plus a number of breakdowns at some earlier time times the probability of breaking down in the remaining time and integrated over all possible times. And so you can solve this in the Laplace domain, and once you have it in the Laplace domain, you can invert it and get the number of breakdowns as a function of time. So after all this calculation, the result is very simple and kind of amusing. So here is our objective function that we want to optimize. And so I'm plotting objective function as a function of this Peclet number, which is essentially your tendency to floor the accelerator of the car. And what one sees is, first of all, there is an optimum for different values of the cost function, the cost for each breakdown. And here it turns out to get a reasonable number, we're defining a cost prime, which is the total cost divided by the diffusion time. So we get numbers that are of order 1. And what one sees here is that when the cost of a breakdown is really small, so it's low cost here, the optimum is way out here at high Peclet number. And also you have a very high objective function. What this means is that if your car is a clunker and it only costs like, you know, $20 to fix it, you might as well just break it down every time you take it out because it costs nothing to fix it. So this is the range in which the cost breakdowns are cheap, so you want to always have your car almost driven to breakdown. On the other hand, you see that if the cost is high, which is over here, so this is thinking about, say, your typical F-35 jet fighter, which, you know, costs like $100 million and costs like, you know, $100,000 an hour to fly it. So you don't want to break it down because, boy, you're screwed if you do something bad with it. So the point here is that breakdowns are expensive. You drive the system away from breakdown, and this is sort of the very cautious approach to dealing with this. So one sees here a very simple, you know, conceptual model in which one has a very rich behavior as a function of the protocol of driving the system. Okay, so the last part of my talk, I wanted to just describe a very simple model of economic evolution by first passage resetting. And in particular, I want to understand the role of altruism versus individualism in first passage resetting. And so this model is inspired by a very beautiful paper by McKean and Shep in 2006. These two guys are really well-known probability theorists, and they came up with the following very beautiful problem. Imagine that your amount of money in your pocket is the one-dimensional coordinate of a random walk. And imagine you have two people who are evolving their money just by random walk process. Sometimes you gain $1, sometimes you lose $1, and if you reach the origin, you're broke, you have no money left. And there's one more feature to this model, which is that there is God above, looking below at these two schleps who are like randomly walking around in this one-dimensional, you know, economic space. And God has one unit of velocity that she is allowed to apportion to these two people in the way that she sees fit. What is the optimum strategy that God should adopt? And it turns out, so what McKean and Shep did is that they solved this problem for only two random walkers. And it turns out that the problem is actually more complicated than you think, because what do you mean by optimizing the state of the system? If you want to optimize the chance that both people are still economically viable at long time limit, then what you should do is, and I'm now using the words in their paper, it's not my words, they use the Robin Hood strategy, give all the money to the poor. And that turns out to maximize the probability that both people are still viable at long time. On the other hand, if you want to maximize the total amount of money in the system, you do the George Bush strategy. Their words, not mine. You give to the richer. And so that was their inspiration. So now I want to use that inspiration to define a very simple first passage resetting problem that contrasts altruism with individualism. So in individualism, we imagine we have two people that have a certain amount of money, and this is what happens as a function of time. And if their money evolves by random diffusion, then we already know what the answer is. We've learned that in one-dimensional first passage, you will always return to the origin. It might take infinitely long, but you'll always return. And so what happens is one guy goes bankrupt, then the other guy goes bankrupt. And that's the end of the story. But if we have altruism, and so how do I define altruism here? So altruism is that we start the same as before, and when the first guy goes bankrupt, so I go bankrupt, I look at Satya. Satya and I know each other a long time, and I say, Satya, I'm bankrupt. Can you help me? And he says, of course I'll help you. I'll give you half of all of my money so that we start life again with equal amounts of money. So that's what happens. We just share our money equally. And then Satya goes bankrupt, and he said, listen, Sid, I gave you half my money. You better give me half of your money. So of course I'm going to do that. And so we just do this and continue on ad infinitum. And so now the question is, what is the dynamics of this process, and which strategy, individualism versus altruism, which is better? So let's try and work this out. And so this is what we did with Benjamin and Julian in 2021. Okay, so first of all, let's do the dynamics of individualism. So it's, again, a very fun game in first passage. Once you're used to the game itself, it's a very pleasant calculation. First thing I want to compute, what is the probability that the first person goes bankrupt at time t? So for the first person to go bankrupt, this is the probability that somebody goes bankrupt at time t. That's a good old first passage probability. And this error function is the probability that one other guy has not yet gone bankrupt at time t. It's the integral of the first passage probability from t equals time t to infinity, which is the probability that you haven't yet gone bankrupt. So that's what I already said. One person goes bankrupt at time t. The other guy is still solvent at time t. And the crucial point is that in the long time limit, this is a t to the minus 3/2 tail. This has a t to the minus 1/2 tail of the long time limit. So this asymptotic decays like 1 over t squared. So even though one guy going hitting the origin, the probability distribution has a t to the minus 3/2 tail, when I have two of them, because you're conditioning on one guy not going bankrupt, the first guy going bankrupt actually goes bankrupt a little quicker in some sloppy sense, because it's a t to the minus 2 tail. And then we can ask, what's the probability for the second bankruptcy at time t? And again, we need to have one guy going bankrupt at time t and the other guy already having gone bankrupt at time t. So it's a complement to this guy, the error function complement. And so this has our good old t to the minus 3/2 tail. So the first guy going bankrupt happens, even though the average time for this event is still infinite, logarithmically infinite, rather than power law infinite in the size of the upper limit. This guy will go bankrupt, the second guy goes bankrupt, and that's basically the end of the story. Bankruptcy is assured. Okay, so now I want to turn to the dynamics of altruism. By the way, how much time do I have left? Roughly. 5 minutes. Great, thanks. Okay, so in altruism, let's represent the wealth of one guy as the horizontal axis, the wealth of the other guy as the vertical axis. And so we start at some point, let's say we start each with $1 in our pocket. And so we evolve by a random walk. So this is a very terrible way of representing a random walk, but eventually one guy goes bankrupt. And what happens is we share equally. So at the first bankruptcy, since we share equally, we just go back to the 45-degree line where equal amounts of money on both sides, for each person. And then we start again and we do a random walk. And you see that in the first case, we started at 1-1. We ended up at like something much less than 1-1. But then after the next bankruptcy, we end up a little bit better off than we were before. And so what we want to understand is the dynamics of starting at 1-1, after one bankruptcy here, it's two bankruptcies. What is happening to this random walker on this 45-degree line? That's the key to the problem. And so the thing is that what we want to ask then is, what is the probability that we have like bankruptcy of our entire society of two people? But here, bankruptcy, we have to put in a cutoff, because in principle, we could go to like 10 to the minus 20th in money, and then we would say, well, we're not bankrupt. But the point is that if we each have $1 in our pocket, if we have less than 1 cent, there's no currency that's less than 1 cent. So let us define 1 cent, or we could define 1/10 of a cent, or a thousandth of a cent. We define this small region as when we reach joint bankruptcy. So when we get down to here, we're no longer economically viable, and that's the end of the story. So what we want to then compute is what is the wealth distribution at each one of those individual bankruptcies? What is the wealth distribution of the solvent agent at the first bankruptcy? So what we need to do is say, well, here's the probability distribution. Again, the sum of the Gaussian and the anti-Gaussian of the guy who's still alive. This is where he is as a function of his wealth. And then we have to multiply by the probability that the other guy went bankrupt at time t, which is the first passage probability. And then we just do the integral. And what comes out of this is a very beautiful probability distribution, this thing which has a 1 over x to the 3 tail to it. And the interesting thing about this is that the average amount of wealth when one guy goes bankrupt, the average amount of wealth in the entire society is the same as you started with. It has to be the same because there's no process in which somebody is gaining money or losing money. Each guy is just doing a random walk. But, and this is the real but, the typical value, typical of the way I defined it several slides ago, is decaying like 1 over the square root of 2 every single time a bankruptcy occurs. So even though the average wealth is staying the same, the typical wealth is inexorably going to 0. And so you're screwed according to this. So now, which strategy is better? So let's compare the case of 2 agents, first of all, because that's a case we could solve analytically. And so this is kind of a busy slide. What I'm plotting here is as a function of time, the wealth of the society. And first of all, let's do the altruists. So altruists is the people, who share their money equally. And it turns out that one altruist, his or her wealth goes to 0 at a time of the order 2 diffusion times. And so 2 of them together have twice the wealth. And so this is the total sum of the society. On the other hand, for the individualists, the first individualist has a much more rapid decay of his or her wealth, and so it goes down fairly quickly until he or she goes bankrupt. And the second guy has a longer tail, and so at early times, it's better to be altruistic. At longer times, individualism wins. You can do the same calculation numerically for 4 agents, for 16 agents, and the crucial point, which is maybe for those who are more socially minded, is that for short times, altruism is always better in this toy model of economic wealth sharing. But in the long time limit, individualism wins in the sense of the George Bush strategy. There's more money in the system, but very few people have all the money. Okay, so I'm at my end. So first of all, I hope I've convinced you that first passage resetting is kind of a cool and new type of stochastic process, and it's been very, only very recently explored. I showed you how to compute the probability distribution by some slick tricks involving renewal theory and path decomposition. I talked about optimization in a toy model. And what's missing in all of this is more realistic modeling and more realistic control protocols, because not everybody is a 16-year-old hormone-charged teenager who slams down the accelerator when they get into their daddy's sports car. I also talked about a very idealized model of wealth sharing. And first point is that we saw that depending on, if you just talk about total amount of money in the system, well, maybe it's better to be individualists, but maybe that's not really the right definition of better. And certainly we want to do modeling with more financial realism. So thanks for your attention. I'm glad to take questions.
First of all, thank you, Sidney Redner, for a very beautiful and excellent talk with an excellent analogies. So now we will take some questions.
Yeah, thank you very much for a very wonderful talk. So here in your case, you ask this first process to a given level L and then you reset. But suppose I put a box, let's say minus L to plus L, and if I say that if it reaches any of the level, I just reset. So then probably it will reach a steady state, right? Do you know the answer?
Well, okay, I've not thought about that. Anyway, I didn't think about that particular case of a finite box, but you're absolutely correct. It will go to a steady state, and yeah, I mean, seems like interesting to study.
Okay.
Yeah.
More questions?
So if I understand well, in the definition of your objective function, you took a linear form. So the closer you are from that level L, the better.
Right.
Have you tried to look at what happened for other forms like quadratic or?
No, we did not. I mean, I guess the point is that we know how to do the calculation, but I guess the main point in this sort of very stupid model of the protocol itself is that we'll have qualitatively same behavior, it'll just be quantitatively different.
Okay, thanks.
Are there more questions?
In the case of that model, is it clear that bang bang is somehow optimal, or?
Yeah, well, it's not clear, but people who work in optimization theory have shown that bang bang is the best. I mean,
In that particular case?
Yes,
Okay,
exactly.
thank you very
Yeah.
much.
So are there more questions? If there is no more questions, I have one, but I can ask you later because we are already running a little late in time.
Whatever you want.
Let us thank Sidney Redner and our next speaker is Sanjib Sabhapandit from Ramanujan Institute, India. So title of his talk is Freezing Transition in the Barrier Crossing Rate of Passive and Active Particles.
Okay, thank you. Thank you. Okay, thank you. First, I'd like to thank the organizers for inviting me for this wonderful conference. So this is my first time in Guadalajara, also in Mexico, and I think I feel like at home. And although I don't speak the language, but like I come from India, and apparently there are 780 languages. That is what I learned, and I speak almost none of it. So I think I'm fine. Yeah. So okay. So this is a talk. So this is a joint work with Satya Majumdar, who is there in the audience. So I'm going to talk about a novel freezing transition we observe in this barrier crossing rate. So which is actually a very old problem, this Kramer's barrier crossing rate for a Brownian particle. And okay, this work has been published here. So let me just start with a plan of the talk. So I'll just start with a statement of the problem with some motivation. I'll first give you the main results. Then I'll give you the basic arguments and then illustrate with some examples. And if time permits, at the end of this, then I'll talk about some extension to active particle, in particular for a specific model of active particle, which is known as the run and tumble particle, and then I'll conclude. Okay, so I think all of us know what is this Kramer's problem. So let me just, for the students, let me just describe it briefly. So imagine that, okay, you have this underdamped, overdamped Brownian motion. So it's in a potential, and imagine that this potential is of this shape. Okay, so you start from the somewhere at the bottom of the potential, and you ask, okay, so these particles are doing Brownian motion here, and with a certain rate, it will escape the potential through this barrier. Okay, so the question is basically what is the rate? This we call it kappa of A, at which this particle crosses the barrier with a relative height which is given by delta of U. Okay, so this is a celebrated Kramer problem, and it's cornerstone of fundamental physics, and it appears across all disciplines basically. Okay, so in fact, Kramer estimated this rate way back in 1940. In fact, there were people even before Kramer which did this calculation. And so what they found is that if the barrier is very high compared to the this energy kBt, then these particles almost reach a equilibrium state at the bottom of this thing, but they still escape. So assuming that, okay, it's like an equilibrium state, and then you just compute the flux across the barrier, and what they find is that this escape rate is basically given by this Van 't Hoff Arrhenius form. Okay, so that's, I mean, all of us will learn this. In fact, there was another approach to estimate this rate, and this predates even Kramer. So look at this first passage time to this object, and this is a mean first passage time. We already know what first passage time is after this Sidney Redner talk. And so basically imagine that, okay, you're starting from somewhere there, let's say at the origin, and this Brownian particle in this potential it wanders off, and at some point it hits this barrier. Okay, and when it hits there, it just goes downhill because it doesn't need anything, this thing. So you can ask what is the first time it hits there and the mean of this first passage time. So the inverse of this mean first passage time is another rate of this escape rate, and in fact it turns out that this first passage time in a potential, so unlike in a free case where the mean is infinite, in a potential this first passage time is finite, and in fact you can compute it exactly for any potential. Okay, imagine that this, okay, given that this potential is sufficiently confining. Okay, and again you see that at large barrier height, it has this basically Arrhenius form, or 1/2 Arrhenius form. Okay, but as we all know that this mean first passage time is just the first moment of the first passage time probability density function. Okay, so in general this probability density function contains much more information just than the mean. Okay, so now therefore this will contain much more information, and in particular if this potential is sufficiently confining, so what one expects is that, okay, this is correct, definitely the cumulative first passage time density is also known as the survival probability. Okay, and this we expect it to decay exponentially, and this decay constant theta of A, it gives another estimates of this escape rate. Okay, and while this mean first passage time can be computed explicitly for arbitrary potential u of x, finding this theta of A is much harder. In fact, there is no general formalism to compute this theta of A for any generic potential. Okay, so to just summarize, so we have these three estimates of the first passage escape rate over a barrier. So one is this Kramer's estimate. The second is the inverse of the mean first passage time, and third is the decay rate of the survival probability theta of A. Okay, so we expect that all these three estimates to converge to this Van 't Hoff Arrhenius form when the barrier height is very large, but in many situations the barrier height need not be very large. Okay, and therefore you expect that, okay, this first rate, this Kramer's estimate is not going to be valid anyway if the barrier rate is not high, but okay, mean you have the 1/, mean first passage time and one this theta of A, so these two you expect it to be different. Okay, and so they will have different dependencies, and indeed what we find is that this theta of A, which is basically the exponential, it gives the exponential decay of the survival probability, it shows rather rich and robust A dependence. A is basically the location of the barrier. Depending on the how this potential u of x increases x as x goes to minus infinity. So your barrier is on the positive side, and you ask how is this u of x decays, increases as x goes to minus infinity. It's still confining, but what is the increase? Okay, so I'd also like to give a remark about this theta of A. So although I have posed this problem as a escape rate problem, as we know that the first passage time in fact it's much more generic and it has much more application, and it's basically estimating this theta of A is it's a rather broad interest, for example. Okay, so I don't have to give motivation to the first spaces time problem after this wonderful talk by Sidney Redner. Okay, so the take-home message is that basically this is basically the main result. So what we find is that the cumulative first spaces time density or the survival probability, so it decays exponentially, and this theta of A shows different behaviors depending on how is the negative side of this potential, basically when x goes to minus infinity, increases this thing. So in the case 1, if its potential increases faster than mod x as x goes to minus infinity, so then what we find is that this theta of A increases monotonically as you basically reduce the distance to the barrier. So if A, you start with infinity and then you reduce A, so it increases monotonically, and then finally, okay, it hits some constant value. So you see that one of our mean first spaces time also, it has a similar behavior, but then it diverges as basically this A goes to 0, because the mean first spaces time goes to 0, so the one over mean first spaces time diverges. So on the other hand, if it decays like a mod x when x goes to minus infinity, so what you see is that as you reduce the distance to the barrier, so you basically move the barrier closer to the origin, so it increases monotonically, and then there is a critical value AC at which it freezes to a constant value, and after that, even if you reduce the A, so what you see is that it basically remains constant. Okay. On the other hand, in third case, if U of A increases slower than mod x, it still increases because it needs to be a confining potential. It increases slower than mod x, that what you find is that theta of A is exactly 0, it's identically 0. So which means that your survival probability doesn't have an exponential decay, it has a slower than exponential decay. So it can be either stress exponential or it can be a power law decay basically. So let me give an argument for why you expect a non-zero theta of A or a 0 theta of A. Okay, so you have this Lange equation, which is a stochastic differential equation, and corresponding to this Lange equation, you have a Fokker-Planck equation. Okay, so you have to solve this Fokker-Planck equation with this boundary condition, because if you start with the already at x equal to A, because you already hit the barrier, so you die immediately. So you have an absorbing boundary condition at x equal to A. But then it cannot also, it has to, it's a probability distribution. So when x goes to minus infinity, basically this has to vanish. So it's a second order differential equation, and you have these two boundary conditions, and you also have an initial condition. So initial condition is that, okay, you can simply take it to be, you start with a x equal to 0 at the origin. So P of x0 is like a delta function. So given this differential equation and this initial and boundary condition, you have to solve this for P of xt, and once you solve it, you have to integrate from minus infinity to A, and that gives you the survival probability. So this is a formal, but okay, it's not always easy to solve this for any generic A. Okay, but this is basically the steps you have to do. So if you do like this, okay, it's not very evident why, I mean, what is this theta and where is it coming from? So it's instructive to do it in another way. So what you do is that you can do a transformation. So what is a transformation? You take it P of xt to be, you multiply by this guy, and then you call it this psi of xt, and you see that this psi of xt basically satisfies this Schrodinger equation. So now you have basically transformed your classical problem to a quantum mechanics problem in imaginary time. Okay, and so this is your initial condition, and this is your boundary condition, and this boundary condition is basically essentially you have a infinite potential at for x greater than equal to A basically. Okay, and your quantum potential now is related to your classical potential by this relation. So now you know that in your from your quantum mechanics that okay, your psi of xt, you can write it in the eigenbasis of this energy eigenbasis, and where these are your wave function. And if there is a ground state, if the ground state is bound and it's separated by a gap, finite gap, so what you find is that your psi of xt will be given by exponential of minus ground state energy times the t. So your p of xt therefore also will go like exponential of minus E0 times t. This is the ground state energy. And when you integrate this guy, so which is your survival probability, so which is given by this. So your theta of A is the ground state energy of the corresponding quantum problem. Okay, so this is what it says that okay, you have a non-zero theta A if basically you have a ground state bound state and that is separated by a gap. So now let's see what happened to our problem. Okay, so this is our classical potential and this is the corresponding quantum potential. And now you see that if your classical potential increases faster than mod x when x goes to minus infinity, so in the corresponding quantum potential will also increase as x goes to minus infinity. So your quantum potential is a confining potential. So and we all know that if you have a confining potential, you have nice spectrum. You have basically only bound states. So you have a discrete spectrum, and therefore you just have to look at the ground state of the that energy. Okay. So on the other hand, if it goes like mod x as x goes to minus infinity, then what happens is that your quantum potential, so it has a single bound state, and then you have a continuum of states basically. So now what happens as you reduce A, the location to the barrier, so you basically reduce A from infinity, and you just keep on reducing, your ground state energy increases, and at some point basically it hits the bottom of the continuum spectrum. And once it hits the bottom of the continuum spectrum, it can no longer increase. And that's when your theta A freezes basically. So your theta A initially is this ground state energy, and at some point it just hits this thing, and this is your critical A equal to AC. After that basically your ground state energy remains same. So on the other hand, if your U of x increases slower than mod x as x goes to minus infinity, so then what happens is that your quantum spectrum is a continuous spectrum. You only have scattering states starting from all the way from 0 to infinity, and you know that if you have only scattering states, okay, you don't have any bound state, so your theta of A is exactly 0 basically. You have basically your ground state energy is 0 and it always remains 0 basically. Okay, so let me now, okay, this is okay, probably most of you are already convinced with this argument, but let me give you some representative cases where you can do actually some exact calculation and you can verify this. Like for example, if you take, okay, you take this thing, okay, since I want to argue that it only depends on the negative side, so I'll just keep the positive side same for all these three cases. And this negative side, in one case I'll take a quadratic potential, in one case I'll take a mod potential, and one case I'll take a log potential. Okay. In log potential, I'll take this C such that your confining potential still gives you a steady state. Okay, and you can do the calculation. Although you can do this calculation by this quantum mechanics way, but you can actually simply do it by writing down something called the backward Fokker-Planck equation. So where x0 is your starting position. So you write what is the survival probability up to time t starting with x0. Okay. So which is the initial condition is that you survive at time t equal to 0. And also you have this boundary condition that if you start with minus infinity, you survive. Okay, it takes infinite, you survive always. And if you start with the location of the barrier, you immediately die. So basically your survival probability is 0. And you need to solve this differential equation for this generic potential with this boundary condition and this initial condition. And one of the simplest way to solve is basically you go to this Laplace space, and in your Laplace transform method, so what will give is that it's basically given by this, and here it is f tilde also happens to be the Laplace transform of the your probability density function of the first spaces time. Okay. So now what we find is that for these three cases, this Laplace transform have qualitatively different behaviors. Like for example, is the first case where it increases quadratically, basically increases faster than mod x. So what you find is that your Laplace transform has only simple poles, okay, and the simple pole represents basically your quantum energy spectrum, okay, and then you see that basically this your as you change A, this pole changes, and this guy is basically giving you your theta of A, okay, and you see that as your A changes, it basically, okay, it increases and gets something like that, okay. So on the other hand, if you take mod x on the left side, so your what do you have it? You have a simple pole, and then you have a branch cut, and this branch cut basically represent, in the quantum case, you have this all this continuum of states. Basically, you have these scattering states and one single bound state, and this is the pole, and this. So now what you see is that as you reduce A, this pole moves from here to here, and that at some point this pole hits the branch point, and then your contribution is basically given by this point. So this is this freezing point, after which basically your theta of A is just given by value at this point. So therefore, if you look at your survival probability, so leading order is basically given by this one for A greater than AC. So this is basically given by this guy. And for A less than AC, basically it's just given by this point. Okay. So this is, okay, you can just basically how to extract this theta of A. So what we do is you basically find out the slope of your survival probability, how the survival probability decays, slope rate, and you see that if you plot it there, it initially increases monotonically, and then it freezes to a constant value. Okay, so therefore your theta A is for A less than A greater than AC is given by this minus negative of this simple pole, and for A less than AC is given by this negative of the branch point basically. So another case, so I need to show that it doesn't depend on the how you choose your potential on the positive side. Okay, it's only depends on this whatever the x goes to minus infinity, and you have a similar behavior basically. Okay, so the third case where your potential increases slower than mod x. So in this case, we took it to be a log of this thing because you can solve that problem. And again, what you see is that if you look at if you analyze this Laplace transform, what you see is that, okay, depending on this new parameter, which depends on the diffusion coefficient and this C, which is a coefficient of the log potential. So you will have some finite moment of the first spaces time, and then you will have a singularity. Okay, and this singularity basically determines how your first spaces time decays. So in this case, it happens to be a logarithmic. It happens to be a power law decay. Okay, so your first spaces time basically has a power law decay, and this nu depends on, okay, whatever this thing. Okay. So in some sense, another way of looking at this is as you know that your power law, you can also write is this integral. So you see that this power law decay in some sense basically represent your continuum of states with a whatever density which goes like e to the power nu minus 1. So you have basically this your continuum of states, and when you sum this continuum of states, basically you have this power law this thing. Okay, you can check for another case. For example, if you take a potential which goes like square root of x as x goes to minus infinity. So in that case, you have a stress exponential decay, so which is slower than exponential, which means theta of A is 0. And again, here you see that if you just look at this square, you can actually write it like that. So you have a continuum of states, and your density of states is density of energy is basically given by that. Okay, so to conclude this part 1 is basically that, okay, so your first spaces time probability density, it has an exponential decay in a confining potential, and this decay rate theta of A has different quality behavior depending on how your potential, confining potential, how it falls on the negative side basically. Okay, so in particular, if u of x increases like mod x as x goes to minus infinity, so what you find is that your theta of a, so it increases monotonically as you reduce a, and at some point a equal to ac, it freezes to a constant value and then it remains. So it has a freezing transition at a particular value a equal to ac. Okay, so I think I have some more time, I guess, right? Yeah. Okay. So what I want to do now, so I want to see, okay, this is for the Brownian motion. So I want to see how generic is this thing, and nowadays there are there is a lot of interest in what we call this active particle. And what is active particle? So let's first tell you what is a passive particle. This Brownian motion, which the problem I just discussed earlier. So that's usually in this literature called as passive particle, where your delta of x typically it goes like square root of delta t. Okay, so your displacement scales with square root of delta t, and this is some random number drawn from Gaussian distribution. But these active particles are like bacteria or genus particle. These are self-propelled particles, and they are the displacement scales at short time is like a ballistic scaling. So delta of r scales like delta t times some unit vector, and this unit vector has its own independent dynamics. Okay, so it has a stochastic dynamic. So it basically it goes along this unit vector n, and it undergoes some kind of stochastic dynamics. Okay, so one of the simplest model of this active particle is called this run and tumble particle. So which basically, okay, you draw a time from an exponential distribution and you move along a constant direction for that amount of time, and after that time you basically what is called this tumble phase, you basically pick up a new direction from all available direction, and again draw a time from an exponential distribution and you again move for that amount of time. Okay, so in 1D even this model is even simpler, so where basically your d of dx dt equal to your some speed times this sigma of t, which is this dichotomous noise, which takes basically value +1 or -1. Okay, and these durations are drawn from an exponential distribution. So what you do is basically you keep going in one direction, and then at some rate you just completely flip, and then you basically go in the opposite direction, and you keep on doing this thing. Okay, and so in fact it shows rather interesting behavior if you put it in a confining potential. It has a non-Boltzmann type distribution. In fact, recently we have studied this model, and what you see is that so this in fact the steady state distribution is exactly known for any potential for this model. It was known earlier, but what was not done is basically analyze this distribution for different kind of potential, and so this is what we did here. And you see that actually if you take a potential which is, let's say, alpha mod x to the power p, so it actually undergoes some kind of a shape transition. So if p is greater than 1, so it goes something like an active phase to a passive phase. Okay, so a passive phase means basically your distribution decays to 0 around the boundary of the basically when you go far away from x, but in the active case basically you find more particles away from the origin in some sense. Okay, this is with Satya and some other people we recently did. Okay, so in particular for if you just take this this a quadratic potential, so you see that it has undergoes this shape transition. This is your stationary distribution, and it undergoes this shape transition. So this is like a passive system, and this is like an active system. But what I want to point out that this probability distribution has a finite support. So it basically bounded by minus v0 by mu to plus v0 by mu, except for the case p equal to 1, where this is like a mod x. So in this case, depending on alpha and v naught, you can either have a completely delta function or you can have an infinite support. So since I want to study this problem for this active particle, and since we saw actually that even this other case in the only in the mod X potential you have this shaped this freezing transition. So we want to basically study this run and tumble particle with this potential. And okay, so this is the stationary state that was already known. This is paper we did. So what you find is that if alpha is greater than V0, actually your stationary state is just a delta function because everything collapsed to the origin. But on the other hand, if alpha is less than V0, so you have a delocalized state, and so this support is basically you have for all the way from minus infinity to plus infinity. So it is basically this thing. So now we want to ask the same question for this potential. So you have this potential and you have this run and tumble particle, and you have this barrier at some point ask, and you want to ask basically what is the escape rate, or what is the first passage time distribution up to that point A, and what is the decay exponent theta of A. So this is what I did with this Sujit. So you can again write down this backward Fokker-Planck equation for the survival probability. So I'll not go to this how you do that. So you have this initial condition and you have this boundary condition. And so the boundary condition is that, okay, if you start with x equal to a, you start with a positive velocity, you immediately die, because if you are here, you just immediately cross. But if you start with x equal to a with a negative velocity, you don't know. That boundary condition is not specified. Okay, so you have basically you have these two boundary conditions. This is initial condition, and then we have to solve this Fokker-Planck equation. So it turns out that you can still do that, and you find your survival probability. So it has an exponential decay, and this theta of a undergoes a similar freezing transition. Okay, and to summarize, basically your survival probability. So it has, for a greater than AC, it has this behavior. So which comes from the, again, if you look at the Laplace transform of the survival probability, it has this simple pole, and then it has a two branch point. So in the earlier case, this branch point was at infinity, minus infinity. So you had earlier you had a full branch cut from SB to minus infinity, but now you have a, so in some sense your continuum state is basically bounded here, okay, not all the way to infinity, and you have a simple bound state in some sense. And you see that this theta of a basically, okay, for a up to some value AC, so it's given by this contribution from this pole, and after that basically it just comes from this branch point basically. So in fact, now you have two this you can also find out the 1 over the mean first passage time, and you see that, okay, for large a they agree with each other, but then as a becomes smaller, this guy freezes, but this guy keep on increasing still. Okay, so survival probability you can actually compute. So I didn't give you the expressions, but you can actually compute the asymptotic, and you actually see that this matches quite well with the this thing. Okay, so you can also find the mean first passage time in this case explicitly, and which is basically given by this. Now you have two mean first passage time starting from the origin, either with a positive velocity or a negative velocity. So you have these two mean first passage time, and of course you can take the diffusive limit, and then you basically reach whatever is known for the Brownian particle, right? And okay, so this is basically say that, okay, so for large, so if your if your survival probability has a exponential decay, so you expect that because it's just the integral of this guy, so your mean first passage time should be 1 over theta a. So this is what happens like for large a, and then okay, you see that 1 over t and theta a, they coincides for large a, and again, okay, in the diffusive limit basically there does it reproduces the diffusive limit. Okay, so the main message of this talk is basically that for both passive and active particles, so if you have a potential which behaves like mod x as x goes to minus infinity, so then you see a novel freezing transition that occurs at a equal to AC. So it means that if you reduce the barrier point, you have a barrier at x equal to a, so you reduce from infinity and you keep on reducing. There's a particular value a of AC where theta of basically, so theta of a is increasing monotonically, then it freezes there, and after that it keeps freezing. Okay, so So we found it quite surprising that given that this Cramer's problem is quite old and it has been studied quite well in, I mean, like if you go to chemistry, I mean, like it's all about Cramer's escape rate actually. And we found it quite surprising that, I mean, this unusual freezing transition of this decay exponent of the theta of A has been missed for, I mean, so many years actually, yeah. And yeah, so this is what basically we did, yeah. Thank you very much for your attention. Yes.
Thank you, Sanjib, for the excellent talk. Now we'll take some questions.
The Cramer's formula also has a prefactor,
yes,
which is the fluctuation determinant of the curvature.
Yeah, exactly. Yeah.
And it seems that you didn't take that into account. And I would think certainly when theta A is equal to 0,
yeah,
it becomes important. Can
yeah,
you comment on this?
Yeah, you're right actually. Cramer's escape also has a prefactor, but that prefactor also depends on whether your potential has a second derivative 0 or this thing. But that's basically the, so what we say is that since Cramer's rate is anyway for large barrier, so which is in our sense when A is very large, so this prefactor is, I mean, in some sense already there in our case, because what I meant is that so you actually, if you see that this so yeah, so as you see that for large A, so 1 over T and Cramer's rate, they anyway coincide. So I'm just comparing with 1 over TA. So this theta of A and 1 over TA, they coincide. So this prefactor is already inbuilt in our theta of A in some sense, basically. Yeah.
Yeah, I just want to come back to a point you made at the very end of the talk, which is like, how did you even think to look at the potential on the wrong side? Like, what anomaly, you know, inspired you to look there?
Okay, so it's yeah, actually we were writing another paper, and there was a referee comment on that paper, and then we started doing some calculation, and then we basically found this result. It's by accident actually. And then we found that, okay, it's quite interesting. So we are basically writing the referee report, and then it came out as a yeah. So yeah, it happens sometimes. Yeah.
Thanks for a wonderful talk. I have a problem. If you said initially that the Cramer's form, all the formulae should coincide for A large. Now, if the left side of the potential grows less fast than mod X, theta A will be 0 for any A, even large. So how can you make it coincide with Cramer's formula?
Yeah,
in that case.
Yes. No. So when I said this, so I also put this thing that for a sufficiently confining potential. Okay. So that was this fine point there. So what happens is that actually when you write down this Cramer's formula, I think you basically assume that so you basically assume that, okay, you have a potential which gives you some kind of equilibrium states, and yeah, so see this, the Cramer's formula is a case that basically, okay, okay, you have a high barrier, and so you assume that you have an equilibrium state in this potential, and okay, you basically kind of find out the flux. Okay, so that's one measure. So your 1 over TA is another measure. So what I'll say is that, okay, so this measure will coincide with Cramer's formula when your left side of the potential grows slower than mod X. Okay, so your 1 over TA will coincide with Cramer's formula, But what I'll say is that, okay, your TA is not defined. So that's not in that case, it may not be a proper estimate of the escape rate when your barrier height is quite large, basically.
Well, theta A is defined, it's 0.
No, it's 0. So it's not in that case, it's not
enough.
a good estimate for your barrier crossing rate for when your barrier is large, basically. Yeah.
So in fact, comparing theta A and the other is a bad idea when the potential is less confining than.
Yeah, but on the other hand, you can also say that, okay, I want to look at it as a first passage time problem, and okay, first passage time density is still defined. Okay, it might have a power law decay, and it's a still defined problem. So in some sense, Cramer's rate is not the only way to look at the escape rate. So I can look at as a first passage time problem, and these two rates are basically different.
And that's a very nice result.
Yeah.
Thank you very much. Yes.
Yeah.
There are more questions? Okay, if there is no more questions, then let us thank the speaker.
Yeah, thank you.
Could you help me to get out of the Zoom? Yes.
Yes. Let's first remove this one. I'll basically stop sharing. I'll just stop.
Please, yes. Okay, it's se te explico el control, funciona adelante hasta atrás. ¿Quieres probarlo? Ajá. Y ya está con
Our next speaker is Juan Rubén Gómez Solano. He is from UNAM, Mexico City. And title of his talk is Transition Path Dynamics of Colloidal Particles Hammering Energy Barriers.
Hello, everyone. Thank you for the introduction, and thank you to the organizers for inviting me to this meeting. So in this talk, I'm going to present some experimental results on the transition path dynamics of colloidal particles in optical potentials. These experiments were carried out in the out of equilibrium soft matter lab at the Institute of Physics of the National University of Mexico. Well, the outline of my talk is the following. First, I will briefly introduce the problem. Then I will present some results on the mean transition path velocity in viscous fluids. Then I will describe some results on the transition path times in viscoelastic liquids. And finally, I will present the conclusion and outlook of this work. So, well, this talk is rather close related to the previous talk by Sanjib. So the main motivation is the study of thermally activated transitions, which are very common in mesoscopic processes, like in folding and unfolding reactions of macromolecules, or the hopping dynamics of colloids in glassy suspensions. These systems share the property that they have to overcome energy barriers in order to explore different metastable states. And this is achieved thanks to the effect of thermal fluctuations, because they are typically immersed in fluid environments. So, as explained by Sanjib, this problem was addressed by Cramer's in the 40s. So I won't explain this in detail. And the basic idea is just to compute the typical rate of the transition. So the inverse of this time is typically the mean time that the particle or the system needs to wait in a certain state in order to surmount an energy barrier in order to escape. Well, the formula is given here with the prefactor. We have here the Arrhenius exponential term, and this depends exponentially on the height of the barrier relative to the minimum of the initial potential. Well, this problem has triggered a lot of experiments dating back to the 90s with the development of optical manipulation techniques. So using these techniques, it's possible to create landscapes, potential landscapes with several metastable minima separated by barriers. And therefore, this represents a very nice experimental system, a model system to study the Cramer's problem. So typically in these experiments, particles are used, they are visualized by microscopy, and by tracking the particle positions, it's possible to study the rates at which these processes take place. For example, this has been studied for particles in water. More recently, the problem has also been studied in gases in order to investigate. ¿Qué hay que hacer?
Nada, solo espera.
Okay. Well, as I mentioned, there are several experiments on this problem. More recently, sorry, these experiments were performed in gases in order to study the effect of inertia. And very recently in our group, we also studied the escape problem in a micellar solution, which, unlike the previous experiments, does not only have viscosity, but it exhibits viscoelasticity. So we also studied this a couple of years ago. But now there is quite some attention on studying a different property, a different problem of this, about these barrier crossing problems. And this is the so-called transition path dynamics. So this has been theoretically studied mainly in the context of molecular folding reactions. And the basic problem is to forget about the initial or the equilibrium dynamics within the potential wells and to focus only on the dynamics over the barrier. So in this case, it is very useful to introduce the concept of transition paths, which are defined as segments of the particle trajectory as it traverses from a specific location on the barrier to the other side. So the main property defining these transition paths is that the initial and the final points must not be recrossed. So the particle can exhibit reversals because of the effect of thermal fluctuations within this transition region. But the two boundaries, here defined by this minus x0 and plus x0, they must not be recrossed. So they are important because they represent actual successful barrier crossing events, which are different from the escape process, which also considers unsuccessful attempts of the particle to cross the barrier. So that's why they have received quite some attention in this kind of thermally activated transitions. So a very interesting result was derived 2 decades ago about the properties of these transition paths. And this is related to the mean duration of these transition paths. So basically, for sufficiently high barriers, well, here in this case, the barrier height must be defined relative to the initial and the final points of the transition path. And the result is shown here. The mean duration depends basically logarithmically on the height of the barrier. So this is different from the Cramer's formula. And we have a prefactor, which is determined by the ratio between the friction coefficient of the particle divided by the curvature of the potential barrier. So this defines a typical time scale. And there are many, many other theoretical results that have not been explored yet. So this is actually the goal of this talk, to present some of these results in colloidal systems. The main challenge in exploring in experiments the properties of these transition paths is that they are very, very short. So they are much shorter than the typical Cramer's escape time. because they only consist of these successful events. So with single molecule experiments, it's extremely difficult because the typical resolution is a couple of microseconds, but this is also the mean duration of these transition paths. So it's very difficult to resolve the spatiotemporal dynamics within this region. But well, so now I will talk about the way we realized in the lab in order to study these transition path dynamics. So to this end, we created a double well potential like the ones I sketched before. So these double well potentials were generated by splitting a single Gaussian laser beam. We used a green laser into two orthogonally polarized beams. So these beams are focused inside a sample chamber containing a very dilute dispersion of colloidal particles in a liquid. So the particles are made of silica. The diameter is half a micron, and they are surrounded by a glycerol water mixture. The reason of using this fluid is that at room temperature, it has a viscosity which is several times the viscosity of water, so the dynamics will be slow. And this is actually the main idea behind doing these experiments, because we really resolve the transition path dynamics over the barrier. So what we do next is to, well, this is a sketch of the sample, what's going on inside the sample cell. We have our colloidal beads. These are the two beams which are focused by a microscope objective. And because of the effect of the gradient of intensity, the particles will be attracted to the regions, to this focus. So we have two optical traps separated by a few nanometers. And the particles either want to stay here or here. But by the effect of thermal fluctuations, they can exhibit hopping between the two minima. So, well, these are typical trajectories of this experiment. These are this is the time evolution of the x coordinate, which is defined as the coordinate connecting the two centers of the two optical traps. You observe that sometimes the particle is on the left, sometimes it's on the right, and this is because of the thermal activation. Along the perpendicular direction, we do not observe any hopping, so we can focus on the one on a single coordinate. So here, just I just want to show the two-dimensional profile of the potential which can be retrieved from the distribution of particle positions. So this potential actually consists of two local minima represented by these blue regions, and they are separated by this orange region, which has a higher potential. So this represents the barrier. And then the problem will be studied along this line, the white line. So the analysis will be done in one dimension. And this is the typical potential profile. So we have the two potential wells separated by a barrier, and they can be very well approximated by parabolic profiles. So from these profiles, we can compute the typical curvatures of the wells and of the barrier. Well, so this is a trajectory measured over almost half an hour. The typical measuring time of these experiments is 1 hour for a given potential. We can create different potentials just by changing the intensity of the laser or by changing slightly the separation between the two optical traps. So as you can see, we have some large periods of time of stochastic duration when the particle stays on the left. Sometimes they are interrupted by the transition paths, and the particle is able to reach the other potential on the right. So to compute the mean escape, here, as I mentioned, we have two typical time scales. The one I will focus on is the mean duration of the transition paths. So the way we compute this in practice is just to identify transition paths from the experimental trajectory. Sometimes we have these events where the particle is not able to fully cross the barrier, so we neglect them, and we only collect all the transition paths. We determine the duration, and we compute the average. And this is our experimental determination of the mean transition path time. We also have events where the particle dwells in a given potential well. So these are represented in different colors, and by computing the duration and the average over different events, we compute also the mean escape time. Well, so just to check that our system behaves well, we compare the experimental values of the mean escape times with those predicted by Cramer's formula. We observe a very good agreement. So this means that the conditions of a sufficiently high barrier is satisfied in our experiments. But most importantly, we also check that this formula, which was derived like 20 years ago, is satisfied for the mean transition path time. So as you can see here in the scale, the typical Cramer's time is several seconds, but the mean transition path times is of the order of milliseconds. So they are really short and several orders of magnitude shorter than the mean escape times. So we check that even this prediction is satisfied by our experiment. But then we also went further because we wanted to characterize the dynamics within this transition region. So one quantity which is very useful for the characterization of such dynamics is the so-called mean transition path velocity. And the idea behind this is to study the spatiotemporal dynamics of a transition path over the barrier. So to compute this, what we do is just to focus on the vicinity around a certain position. So we define a certain width, and we compute the average time that a transition path spends in this stripe. So this average is performed over all transition paths, and this leads to a value of the mean time that the particle spends performing a transition around a certain position. So if we divide the width of this region by this mean time, then we have the mean transition path velocity. So there is a very interesting property of this mean velocity, and this is that it can be related to probability density functions of the particle position within the transition region. For instance, we can compute the fraction of time that the particle spends along a transition path within this region, this stripe. So for this, we just compute the average time spent here divided by the average time spent along a transition path, which is just the mean transition path time. But at the same time, this must be equal to the probability of finding the particle in this region. So this is related to the probability density function of the particle, provided that it performs a transition path. So by equating these two quantities, we find the following expression, the following relation between the mean transition path time, the mean local velocity, and the probability density function of the particle position in this transition region. Well, so we have now the experimental data, so we can compare with a model. First of all, in the upper panels, I'm showing as blue dots, the experimental results for the mean transition path velocity. So as you can see, it exhibits this interesting behavior. Very close to the boundaries of the transition region, it has very large values, but very close to the top of the barrier, it has a minimum. And this is because the particle, when performing one of these transition paths, it struggles to move around the top. And then, based on a model, for example, we can model the motion of these particles by using the Smoluchowski equation, in this case in one dimension. And after some calculations, we can compute an expression for the mean transition path velocity, which is expressed in terms of the diffusion coefficient, this characteristic time scale that I presented before. We also have the local curvature of the barrier, and we have the height of the barrier. So this is our expression. I show this expression as a solid light here. the different plots correspond to different potentials. So these are actually different particles moving in different potentials. And in all cases, we observe that there is a very good agreement of this mean transition path velocity with this expression. Well, previously I showed also this relation between the probability distribution of the particle position along a transition path and the mean local velocity. So we verified this with the experimental data. This is shown in these lower panels, so they correspond to the same upper panels. The probability distributions are shown in blue. And the blue dots corresponds to the inverse of the mean local velocity. So you can see that they coincide very well, and they actually also coincide with the expression given by this formula. So with this, we explored this mean local velocity within the transition region, which was not possible before because the experiments were performed in water or in different fluids with a very low viscosity. So the resolution was not enough to explore this transition path dynamics. So we also checked an expression which was proposed some time ago, relating the probability density function of the particle position along transition paths with other probability distributions. So we can use the Bayes theorem in order to express it in terms of the probability that at a certain position, the particle performs a transition path. So this is slightly different from this. We can compute this from the experimental trajectories. They are shown here with these blue symbols. The bars corresponds to this quantity that I presented before. And this can also be related to the equilibrium distribution of the particle over a very long trajectory. So this is basically the Boltzmann distribution, which is shown within the transition region as a solid line here. And we have also the probability that during the barrier crossing process, the particle is in a transition path. So this is this quantity here, which can be related to the mean escape time given by Kramers, and is also related to the mean transition path time. So after working with this expression, we end up with this very nice formula, which quantifies the ratio between the mean transition path time and the mean escape time, and is related to these probability distributions within the transition region. So on the left-hand side, we have a ratio of time scales. On the right-hand side, we have probabilities and probability densities. And from the data shown here, we compute the left-hand side. This is shown as triangles. So the red triangles correspond to transitions from left to right. The blue ones corresponds to transitions from right to left. And the stripes corresponds to the right-hand side. So we observe in all cases a very good agreement between this ratio of two time scales. How much longer do I have? Okay, thanks. So a second problem that we address with this kind of experiments is the transition path dynamics in a viscoelastic fluid. So this work we started a couple of years ago, where the idea was to study the hopping dynamics of a particle in a double well potential created by optical methods when the surrounding medium is viscoelastic. So in this paper, we studied the Kramers process, but in this talk, I will present the results on the hopping dynamics over the barrier. So again, we perform this analysis within the context of these transition path times. Well, the main motivation of this is that many liquids in nature are actually viscoelastic. We have here two examples. One of them is a biological fluid like saliva. We have also here the example of a polymer. And the main feature is that they are composed of macromolecules suspended in a viscous solvent. So they exhibit not only viscous behavior, but they also exhibit elastic behavior like a solid. And this happens when they are subject to an external deformation. For instance, when a shear deformation is applied to this kind of solvent, to this kind of fluids, and when we pose especially a step-like perturbation of the deformation like this, they respond differently depending on the macromolecular structure. Typically, they relax, the stress develops, the shear stress develops, and it slowly relaxes to zero, which is slightly different from the behavior in the Newtonian fluid. For example, in the water glycerol mixture I described previously, in which case the relaxation is almost instantaneous. So a quantity which generalizes the concept of viscosity in this kind of fluids is the so-called relaxation modulus, which is defined as the ratio between the stress relaxation modulus and the deformation. So by taking this ratio, we have this G of t. We can also compute the Laplace transform of this quantity, and this defines a frequency Laplace dependent viscosity. So you can see that this generalizes the concept of viscosity because for a Newtonian fluid, this is a Dirac delta function. So if you put this here, this reduces to the viscosity of the fluid. It's just a constant. But in general, in a viscoelastic fluid, this function depends on frequency. Well, so in the experiments, we use two types of viscoelastic fluids. One of them is composed of polyethylene oxide polymer mixed in water. So the second one is a worm-like micellar solution, which is composed of a surfactant and a salt mixed in water also. And well, here I just sketched the main details, but the basic feature is that they actually exhibit viscoelasticity. And by use of microbiology, we compute this frequency-dependent viscosity. So this is for the micellar solution in blue. In orange, I showed the frequency-dependent viscosity for the polymer solution. We can also compute G prime and G double prime, the storage and loss modulus. But for our analysis, it's sufficient to have this viscosity. Well, now the experiments just consist of creating samples with colloidal beads in these two types of viscoelastic fluids. Using the same methods as described before, we determine the profiles of the double well potentials. We focus on the transition region over the energy barrier. We identify the transition paths, and we compute the mean. The duration of these transition paths. So here the goal is to try to describe what happens with the distribution of these transition path times. And to this end, what we did is to use a very old result from the 80s, which describes an effective Fokker-Planck equation for the dynamics of a particle in presence of a memory over a parabolic barrier. Actually, this result is valid for any linear force, so we specifically applied it to the dynamics over the barrier. And the important feature of this effective Fokker-Planck equation is that it involves a function, the derivative of this function chi, whose Laplace transform is related to the frequency-dependent viscosity, which we measure independently by microbiology, and it's also related to the local curvature of the barrier. So we have everything measured independently, so we can use this in order to compare our experimental results with these estimates, theoretical estimates. So here in blue, I show the distribution of the duration of the transition paths. So as you can see, the distributions are non-exponential. They have this maximum, and then they decay to zero. From the previous Fokker-Planck, effective Fokker-Planck equation, we can derive an approximation for the distribution of these transition path times, which is given by this formula. The important feature is that it can be expressed in terms of this function chi, which is related to the viscoelasticity of the fluid. So we put everything from our measurements, and the theoretical prediction of this distribution is shown in red. we observe that it describes very well our experimental results. So just for comparison, I'm also showing the results by using a model without viscoelasticity, just by taking into account a constant viscosity. And this is shown as dashed lines here, and we observe a very large disagreement. So which is normal because this model does not take into account the viscoelasticity of the fluid. Also from the experimental data, we can compute the mean duration of the transition paths. For the polymer solution, they are shown here as a function of the logarithm of the barrier height. These are normalized by this typical relaxation time that I presented at the beginning. So the goal of this is to compare to this formula provided by derived from a purely diffusive model. So in this case, we can normalize by tau 0. So in the case of a purely Newtonian fluid, this only depends on the barrier height, and this is represented as this solid line. But what we observe is that in the polymer solution, there is a very large reduction of the corresponding mean transition path times, normalized by this tau 0. We also observe that there is a very large dispersion of data, and this strongly depends on the local curvature of our potential barrier. So if we numerically use, we can use this expression for the probability distribution of the transition path times. We can compute the average numerically, and it turns out that we obtain this shaded area, and all our experimental data lies within this region. So this model, which incorporates the effect of viscoelasticity based on this effective Fokker-Planck equation, describes very well our results. So we can also check what's going on with the micellar solution. In the micellar solution, we find that the normalized mean transition path times are even more reduced. So this also strongly depends on the particular viscoelasticity of the fluid. And just to check that everything was correct, we repeated our experiments in water, which is a Newtonian fluid. So in this case, we observed that this formula is verified very nicely. Also, we checked that in glycerol water mixtures at concentrations at which the viscosities match the values for the polymer solution and the micellar solution. And in this case, no reduction is observed. We actually observed that this formula holds very nicely. So just to finish the presentation of these results, what we did is to compute an effective viscosity in these viscoelastic fluids during the barrier crossing process. So the main idea is to compute the viscosity that could be achieved by a purely viscous fluid in order to have the same mean transition path time. So this defines an effective viscosity from the viscoelastic data. And we also compute a characteristic frequency given by the 1/2 of the inverse of the mean transition path time. And we plot this effective viscosity as a function of this characteristic frequency. This is the data for the polymer solution. This is the data for the micellar solution. And we compared our results with the rheological curves obtained by microbiology, which are shown by these dashed lines. And we observed that there is a very good agreement in both cases. And the interpretation of this is that when the particle performs the crossing dynamics over the barrier, by thermal activation, it actually excites this frequency at which the viscosity corresponds to the frequency, to the viscosity given by the rheological curve. So here, our fluid is not characterized by a single viscosity, but we have a spectrum which is activated by the transition path dynamics. So with this, I would like to conclude. So the main message is that we carried out experiments in order to study many properties predicted for the transition path dynamics of systems across energy barriers. So we have currently some work in progress. we are studying the mean transition path velocity in viscoelastic fluids that I didn't present here. We are also studying the barrier crossing dynamics of self-propelled particles and anisotropic particles. And finally, well, these are, I would like to acknowledge my students, my collaborators at UNAM. We received funding from UNAM. And with this, I would like to thank you for your attention.
Thank you for the talk. We will take some questions now.
So one of the main conclusions is that viscoelasticity of memory can make transition faster. And what would be, let's say, the qualitative or physical explanation of that behavior, and whether this behavior is general or it can be something else sometimes.
Yeah, well, the physical explanation is that when the particle is activated by a thermal transition, well, the particle is in a viscoelastic fluid, so there is also some energy storage when performing these transitions, and they somehow promote the escape over the barrier. So once this happens, the particle activates the characteristic frequency, and then the particle explores this characteristic value of the viscosity, which depends on frequency. So this would be the physical explanation of the effect. So it's actually very characteristic of viscoelastic fluids. So when doing this in the viscous fluids, the theory is satisfied for purely diffusive models.
Any more questions? So if there is no more questions, let us thank the speaker once more. Okay, this was our last talk in this session. So we will go for the lunch right now, and we will be back at 2:50 for the next talk. And then we will have, in that session, we have only one talk. And then we will have a special coffee session, and after that, the poster.
Perfecto. So does it work? Yes.
Welcome everyone for the session after the lunch. So now we have the speaker, Francois Leyvraz. He is from Cuernavaca, UNAM, in Mexico. So just one note, when I came to Mexico, he was my mentor. So it's an honor to present him here. So title of his talk is Scaling in Aggregation and Related Models.
Thank you very much, Shoham, for the very kind introduction, and thanks to all the organizers for the invitation. So I just want to say a few words about scaling methods as they apply and as they simplify things in aggregation. So I'm not going to talk about a vast array of examples because there would be too many. Just give a few simple illustrations of what can be done how. So what I'll be talking about is, on the one hand, well, first, since I'm going to talk about scaling in aggregation, it's probably a good idea to introduce the two concepts. So I'll introduce what I mean by scaling and give a very quick view of what the way we will use to describe irreversible aggregation. Then I want to shortly provide a very easy application where scaling gives, in a delightfully straightforward way, the correct results. I want to also, it's a case where we don't apply the kinetic equations, which I'll be talking about. So it shows that the system is more general than what we ordinarily, or what we straightforwardly call kinetics of irreversible aggregation. Then I want to talk about the general theory of scaling for those kinetic equations. And then in the case of the kinetic equations, I want to show a very curious puzzle, and I will hint at its solution, which I do not yet fully understand. And it involves the case of pure three-body reactions. Okay, so that's the program. So by the way, of course, if anything is totally unclear, please do not hesitate to interrupt. So what is scaling? Well, that's maybe the most trivial example is in thermodynamics. Generally speaking, scaling just means that if a problem has some kind of symmetry under scaling transformation, so under change of scale, when you change several variables in their scale by different factors, then you assume the problem somehow behaves simply so that you can get a solution that is invariant under scale. So the classic example is, of course, thermodynamics in the vicinity of the critical point, and that in that case, the variables which are relevant in the simplest cases would be the difference between the temperature and the critical temperature, the difference between the magnetic field and the critical magnetic field, or the density and the critical density, and finally, the free energy and its critical value. So these values are critical when all the three are 0, epsilon, h, and small f. So you can obviously change scale at that level. And if you do, you find indeed that the free energy here has this kind of behavior. That is, if you scale the epsilons, if you scale the h's, then you also scale f. That is, f is invariant if you scale everything correctly. Now, that's actually a very frequent phenomenon. It happens all the time and you are often led to identify it by a simple study of what happens with units, basically. It's nothing more than that. Now, what's aggregation? What's irreversible aggregation? In that case, you have aggregates. So that can be many things. That can be, for instance, the cream in your milk, when it starts floating, well, it can consist of, if it's not stabilized, it consists of droplets of cream that, when they come together, become larger droplets. Or in, well, the red glass of Tlaquepaque, it has its color from aggregates of gold, which consists of very, very small nanometric red gold particles, which are, when in solution, they are blue, and they aggregate, that is, they start sticking together irreversibly and make very large aggregates up to microns, which then create a red color. And so this process is irreversible. So you have aggregates with M1 constituent elements, aggregates with M2 constituent elements, which give rise to one with M1 plus M2. Or, if you like better to think in the continuum, if the mass of one aggregate is M1 and that of another is M2, then it adds up to M1 plus M2. And then, very often, the speed or rate at which the equation occurs varies in some manner according to the relative sizes. So there is a reaction rate or a reaction rate matrix, K M1, M2, which quantifies the speed at which the reaction proceeds. So typically you say the concentration of M1 times the concentration of M2, which provides some measure of the encounter probability, times Km1, M2 is the rate at which M1 plus M2 gets produced. So that is, however, not always the case. It is, in particular, it can be at all meaningless because it's not at all necessary that the probability of encounter be proportional to the product of concentrations. But still, we get, in very general cases, we can use, even when we cannot use the concept of reaction rate, as we shall see, the approach of scaling actually works. Okay? So now we have an equation, which is the equation of Smoluchowski. I somewhat apologize for the complexity, but just let's look at it very simply. You have here the reaction rate, here the encounter rate, which is the product of concentrations. And here you have a constriction, because of course it will only contribute positively to M if M1 and M2 add up to M. That's sort of obvious. And in fact, there are loss terms when either M1 or M2 are M, but I didn't want to overload the transparency. So, and we won't really need it. Now, to do scaling on this equation is sort of the very first task. So let me do it. The idea is very simple. Usually for reaction rates Km1, M2, you want to be able to be satisfied with a coarse description of how they behave because you don't know in any way. I mean, aggregating systems are usually complex. So you don't know how they behave. So, and you don't want to know. So you want to be able to deduce results from coarse properties. And the coarsest property of the reaction rate matrix is, of course, the degree of homogeneity. So we're going to assume that A has a degree of that K has a degree of homogeneity lambda, and then there is a scaling behavior of those equations. If you stretch the concentrations by alpha, the masses by beta, and the times by gamma, for example, the masses, scaling the masses by beta here gives a beta to the homogeneity degree, which is lambda. Here we get a 2, and here we get a -1. So overall, beta lambda plus 1. And if you go on with this, you see that any invariant solution must satisfy this particular condition. Now that's very straightforward. And additionally, in the cases we'll be interested in right now, the total mass is conserved, which means that the total, Well, the total mass is conserved, which is normal because in every single collision it's conserved. I mean, when M1 collides with M2, you get M1 plus M2. Well, the total mass, the integral of MCM, which we see here, is conserved. That's a very easy thing also to prove mathematically. There are cases, which I don't want to go into now, where mass actually decreases because some part of the mass is unfortunate enough to be swallowed by an infinite cluster. But that's, of course, and of course, when things go to infinity, well, the bookkeeping gets lost. But that's not what I'm going to deal with. So we do need the mass to remain constant. And by the same amount of bookkeeping, you find that this gives you this relation, alpha minus 1 beta squared equals 1. And so when you combine those two, you immediately get this. So if you know one of the three, alpha, betas, and gammas, you can deduce the other two. Not a big deal. So I recall the earlier equations. Alpha is beta squared, and beta lambda minus 1 gamma is 1. So for an invariant solution, CMT should be this, is this, and then when we set these, we get this. So this is a functional equation which the concentration satisfies. And of course, you could immediately get a scaling form of the usual kind by simply, for instance, eliminating this time, for example. So you choose a time-dependent value of beta, which makes this equal to 1. And then, of course, we have an arbitrary function here of one single variable. So that's what I was saying. Scaling consists in eliminating variables and getting things to depend on scaled variables. If you do this, by the way, on numerical work, I mean, if you present CMTs, it's absolutely standard to eventually reduce all those things to a scaled plot, which works wonderfully, at least at large masses and at large times. At small masses and small times, the solution hasn't reached yet its invariant form. But it's important. It's a fact that the invariant form is asymptotically stable. I mean, it's something which normal solutions reach. Okay, so what do we have here? The CMT turns out to be this beta squared. So what I call the typical size to the minus 2. The typical size normalizes the mass in the to be a scaling variable. So we have st to the minus 2 times phi of x. And this, of course, is 1, so it doesn't matter. So we have this set of equations. CM2 is a typical size to the minus 2 times a scaling function of a scaling variable, which should always be taken to be 1. And so this tells you the masses you're going to be interested in grow as t to the 1 over 1 minus lambda. So that's a formula. If you can remember, it would be nice. 1 over 1 minus the degree of homogeneity. That's the exponent with which the typical aggregates grow. So that's it. Typical aggregates grow like this. We have a function which is of order 1, which depends on the scale size. And then to make the concentrations, well, the concentrations have to be a lot smaller because you need a lot of them to add up to 1. So there's this st to the minus 2. Okay. So this is now introducing things which are sort of standard notation. Phi x is usually defined to have a power law. I mean, phi x occasionally has a power law singularity, occasionally not. We'll see that. So x minus tau would be the power law if it exists. The typical size always increases as a power law, or almost always. So t to the z is this 1 over 1 minus lambda. And finally, C1t is t to the minus w. So that's a different thing. The monomers, or the smallest aggregates, have a power law decay. When there is a power law decay in phi, there is also a power law decay in C1. And so that tells me, okay, so there is a connection due to all this scaling picture. C1t turns out to be t to the minus 2 minus tau z. That's sort of evident. I mean, the st to the minus 2 is the factor that comes before the concentration, and this is phi of x, so phi of 1 over st is 1 over st to the minus tau, which with zero calculation gives you that. So eventually you get this connection. W, so that's the exponent at which small particles, very small particles, decay, is 2 minus tau times z, and tau is the exponent which characterizes the concentration profile for small masses. So a typical concentration profile will start off as m to the minus tau. Tau can be negative, so it might start like that, or it might start like that on log-log paper, and then it gets cut off, typically by an exponential cutoff. So m to the minus tau is, at any fixed time, the initial decay in masses of the aggregate distribution function. And so this exponent is here. And this is the typical size, and this is the monomer or small particle decay, and this is the typical increment, the typical size growth. Now, I just want to show you an application in which precisely, actually, the kinetic equations do not apply. That is, the rate of encounter is different from the rate of from the product of concentrations. So it's really a truly correlated system which is somewhat problematic. So the model is the following. You have particles which start out in one dimension, and they move at random velocities, and they move ballistically. So contrary to what we ordinarily have, it's not diffusion. So they move ballistically on a straight line, then of course they eventually collide, and when they collide perfectly inelastically. That means they stick together, the momenta add, and so do the masses. So that's, you might say, it's the simplest mechanical system that more or less corresponds to what I've been doing, to what I've been describing. So particles, of course, of mass m have accumulated a momentum p of m, which is the sum of m random variables. So p of m, the total momentum, grows at the square root. And since p of m is m times the velocity decays as the inverse square root. So it's a nice looking system. You have these particles, they stick, they accumulate mass, and they get ever slower. So how does the typical size grow? Well, here you have a very easy thing. I mean, the rate at which two particles react, independent of concentration. Concentration has nothing to do with it. The rate at which two particles react is obviously the difference between two velocities. And all the velocities are of order 1 over root m. So when you increase by a factor of a the two masses, the rate of reaction of those two masses, no matter how you cook it, will decrease as 1 over root a. So we have lambda is minus a half. And so 1 over 1 plus a half is 2/3. So that's 1 over 1 minus lambda, 2/3, which is in fact a wonderfully well checked numerical fact. Z does indeed go as 2/3. And now can we get any information about the rest? Do we know whether the aggregates follow a power law distribution or whether they do not? And if they do, what is it? So that's the next part of the program. one easy way, we know Z. So if we knew W, we'd be done because tau immediately follows. So how does it? That's a neat little piece of algebra. It's one of the few cases where it's nice to start in the future and go back to the past. Let's assume I have two neighboring particles, both typical, both of size s of t. And I want to know what the probability is that somewhere okay, and now these particles have ancestors. They all arose from monomers which filled out an interval of length s of t. So here also an interval of length s of t, here an interval of length s of t, and here the two extremes connect. These are particles which go towards the inside, and those go towards the inside, and there's nothing here that tears them apart, so they all wind up being particles, being aggregates. Now the question, where can I put something and hope that it will remain a monomer? Well, if I put it here, it's a bad start because it's going to be squished by the two outsides. Same here. So I have to put it here. But the other condition is that I need to put it here, but remember, the velocities go between -1 and +1. If I use either -1 or +1, it's going to crash into this particle or this particle. So I had better choose a small velocity. And how small should it be? Well, it should be just small enough to remain here. So that velocity should be this length over this time. So maybe, well, it should be apparent. This is the way time develops, and these are the x-axes. So the slope here, this 1 over, this is this slope, this inverse slope is the velocity. So let's see how it works out in detail. So if we randomly add another particle, we need two events for it to survive. First, it must be here, and second, it must be slow. Is that clear enough? Okay. So let's estimate the probabilities. The probability that it should be just in between the two domains is 1 over s of t, because the domains have length st, and the intermediate, the interface, has length 1. So here we're done. 1 over st for the first element. And the other one, the velocity, well, is you should not be able to cover a distance of the order s of t in a time t. So the velocity should be less than st over t. So you need those two conditions, 1 over s times s over t. So clear enough, we have that the monomers survive with a probability 1 over t at a given time, t1. But that's true for all times t1, therefore monomers decay at a rate 1 over t. So that gives me w equals 1, and that gives me, since we remember that z is 2/3, and that so that's the growth, 2 minus tau times 2/3 is 1, which with a bit of algebra will give us tau to be 1/2. So it decays, the particle distribution decays as a power law as an inverse square root. So let's just see very quickly the numerics. This is a double logarithmic plot of the concentration of m-mers at time t. This is as a function of m at a fixed time. And the two times are 1,000 and 5,000. So if z is 2/3, 1,000 to the 2/3 tell us that the typical size will be in the hundreds. So that is indeed here the case. So in the hundreds, we have a break. At a slightly later point, we have as well. And these are the power laws which describe the small particles distribution, and they indeed go as m to the -1/2. this straight line represents m to the minus 1/2, and this is how it is. This is not a result that could be otherwise trivially obtained. Independently, some other people, Piasecki and others, found an exact solution for this model. It's a mathematical wonder. So, and they get exactly those results. So it's, of course, they also get results for short times or all sorts of things. I mean, it's a very beautiful exact solution. They get the results for specific initial conditions and all sorts. It's a lovely thing. But we can see how very nicely a pure scaling consideration gives equivalent results. Now, let me shortly what happens with standard aggregation kinetics. So if we do have a K that depends on M1, M2, and if we do have the equations which I wrote back there, then what are the results of scaling theory? Those are a bit tedious to present in detail, but let me show the results. So there's a very coarse characterization of K with its lambda. Actually, to know what happens with the scaling function, we need a bit more. We need to know whether the aggregates of similar size react much faster or much slower than those of widely different sizes. Then that at least will characterize broadly the form of phi of x. In the first case, phi of x actually has a power law, with tau being 1 plus lambda, and the cluster size distribution is therefore broad. There are many, many small clusters because close to x equals 0, phi of x decays as a power law, as a positive or negative power law. On the other hand, if aggregates of similar size react much more slowly than that of different sizes, then somewhat puzzlingly, monomers decay extremely fast. And, well, actually that's, yeah, because the typical size aggregates are fairly large, and therefore they react very strongly with monomers, so monomers decay almost exponentially. And in fact, what happens is that monomers decay as a stretched exponential, and therefore phi x goes to 0. The scaling function goes to 0 as a stretched exponential. There's an intermediate case, which I had best not talk about, which is when they react with approximately similar rates, and that's indeed a case in which everything can happen. For large x, on the other hand, we always have, for phi of x, an exponential decay modified by a power law, which happens to be lambda, or minus lambda, x to the minus lambda times e to the minus x. So we have this rather peculiar feature that the large time behavior has a completely different power law than the small one. And from an analytical viewpoint, it's rather difficult to create that sort of effect. So it's generally true that it's quite difficult to get exact solutions for general lambda precisely for that reason, because analytically, it's a real mess to generate this difference in the small and large mass behavior. Just as a joke, I mean, you might think that this is all very simple. So this is the equation that you need to analyze in order to get anywhere. So that should at least prove that I'm a serious person. There's absolutely no need for you to either understand or have anything to do with that equation. I just wanted to put it there because I don't want to give the impression that it's all easy. So this is an equation involving Laplace transforms and everything you like. Here, I want to leave you with a puzzling result, in my view, 3-body reactions. So you redo the usual scaling argument, which I'm not even going to go through. If you want to check it out, there it is. There you get another form, which is that the typical size grows as 1/2 minus lambda. Basically, this 2 is 3 minus 1. So just as the 1 was 2 minus 1. So binary reactions have 1 over 1 minus lambda. This has 1 over 2 minus lambda. Totally unsurprising. Now, this, of course, is quite as elementary as the other, but it's wrong. So how can it be? Well, that's another question, but it is. You can easily, I mean, there are all sorts of kernels you can exactly solve. In the binary case, the straightforward ones are M1 plus M2, constant, and M1 times M2. So in the trinary case or ternary case, the very first one you might try apart from the constant is this one. And indeed, that's trivial to get. I mean, you get a formula like that, but absolutely not hard. And you can also analyze it by what's called the moment method, which is a lot more efficient. In any case, there's strictly no doubt that the time, the S of t, is integral, which can be defined as the second moment. The second moment goes as t squared. Now, so t squared tells us that z is 2, which is not really in good agreement with 1 over 2 minus 1. So there's a serious problem, right? Z equals 1 is not equivalent to Z equals 2, and there's why. It's a very strange thing. Now, I can just show you. So, of course, if you are doubting that S of t is actually the second moment, then you can quickly read this remark, which evaluates using Cm is st to the minus 2 times phi of x, and you rescale the thing, and then integral x squared phi x is always convergent, and so this second moment is in fact the typical size, which is more or less obvious because some S or the MCM is a probability distribution which is normalized, so m squared Cm summed over is the average mass. And the average mass in that case is in fact the typical mass. So this is the other equation. It's equally pleasant as the first, and there is in fact a very real problem with the singular behavior of phi in this double yz integral, but that's really the last thing I would like to confront you with. So let's see if we can find something more decent. Now, if you think normally, a reasonable kind of scaling would somehow involve that the normal reaction is when three reactions of typical size tend to collide. Whenever there is a lopsided and singular dominance of another reaction scheme, things might be expected to go wrong. In this case, if you work hard enough, you see that C1 remains for quite a long time, and there's a genuine possibility, I need to work out that in more detail, that A1 plus AK plus AL is actually the dominant reaction scheme. So just as it happens in some systems, in some binary systems, that they grow only by monomer addition, and in those systems, indeed, the scaling theory fails, it could be here that essentially the reaction is catalyzed to some extent by monomers, which explains the bizarre result. If it is so, then we can say that there's essentially, and now that is for specialists mainly, I guess, this reduces to a binary reaction in which the kernel is a sum. So we have exponential growth in the effective time, but the effective time is rescaled by the concentration of 1 using this scheme. So you have the exponential of a logarithm, and that's a fairly arbitrary power law, which actually is probably t squared, because there is in fact a factor of 2 somewhere in the exponential growth of the sum kernel. So let me finally conclude. So scaling consists in reducing the complexity of systems with many variables by invariance under scale transformation. It's a very useful technique, and it provides a very broad framework, which is extremely useful. bien. Oh, and I think I have a couple more. Yeah. So you can read those since I'm getting out of my time. Thank you, Shoham. Thank you, everybody.
Thank you, Francois, for the nice talk. So now we will take some questions. So if anybody have any questions.
So three body was weird. I mean, what about higher bodies? Will they all have the same pathology as three body?
Probably. Most probably. I mean, there's not just that for a pathology. I mean, it's horrible. For example, you can solve constant kernel perturbed by M1 plus M2 plus M3. Since both have Z equals 1, it makes more or less sense, except they don't. But and there you get continuously variable Z, whatever. I mean, I haven't tried quaternaries, but I'm reasonably sure that it doesn't depend on the ternary nature. It's just multi-body awfulness.
More questions?
Yeah, okay. Es que soy sordo, entonces.
Is it possible to generalize this approach to these non-binary or like explosive aggregation process where you compare?
I'm trying to do that. It's well, scaling can certainly be done. When you try to do that, you also get a failure of Z equals 1 minus over 1 minus lambda, but explosive percolation is intrinsically multi-body. So that is part of the reason why I said I don't believe ternary is unique, because I've done some quaternary work or on explosive sorts of things. So to say what an explosive aggregation process is, there you take 3 or 4 or k particles, you bring them all to the classroom, and you take the 2 smallest and join them and send the others back. So it's a very strange approach, but so no, the answer is certainly the normal values of Z do not arise. Numerically, they're quite wrong. And they don't depend on lambda only, and we don't know what they depend on.
More questions? If there is no more questions, then let us thank Francois once more. Okay, with this single talk, this session is over. Now we have a special session for special coffee session. And let me announce that special coffee session is to celebrate the 70th birthday of Francois and 70th birthday of Jacob Barbershot and 80th birthday of Thomas Seligman. Now, Thomas Seligman was supposed to be here, but he got his hip replacement a week back. So he couldn't be here, so he will be joining online. And so we have a small arrangement to celebrate their birthday outside. After that, we will have the poster session. So the poster session will start around 4:15. So now our next session is to celebrate their birthdays.
Hi, Thomas. Could you hear us? Thomas, could you hear us?
Put on my mic. I can hear you and I can see you. Hello, Johan? Can you hear me?
I don't have.
I can hear you.
Could you help us? Sure. Okay, then. And Thomas Liebman, my chat, he said that he confirmed. Yeah, okay. Dice que no la vieran. Digo, otra ecuación. Pero no. Es que dice cómo no. Okay. So you remember our WhatsApp? At least you can. Yes. So you remember that at the time we also going to explain the right aggregation and the annihilation problems at the same concept. Yes, and that I learned from you. So and at that time, also I told you that it is there in your paper also, but you didn't. You forgot that you wrote that paper also. Yeah, which is in journal of one paper. And so now the point is that the concentration decay we have statistic aggregation that's equal to we have the same crossing. Now, so that's what actually I try to understand. What I try to understand. You have to aggregate. How it's a different problem. I understand. One quarter. That I'm not sure now. We have all other things remain the same. But one quarter comes only from factor dimension. Now, aggregation with respect to structure. Yes. 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 Statistic aggregation is two velocities, but when you are using half, if you put in perspective, so the need for annihilation is parity particles may annihilate it. Extra particles may create this transmission, which is a pure diffusion on the track. So that's why we get the small form. Right. Now, if you have aggregation, that way. Yes. Antonio. With I'm Tomás, ¿cómo estás?
Hola, Tomás. Hola.
estás?
Bien, bien.
I'm not sure. Okay, we can assume.
¿Qué
Hi,
tal?
Thomas.
Hi.
Hi, Thomas.
Hi.
Okay, so we can
I
start.
hope you enjoy.
Let's go. We need to.
Hola. ¿Qué tal?
Hola, frente, ¿verdad? No nos dio. Hola, Tomás.
Hola,
Buenas
¿qué tal?
tardes.
Hola Tomás, feliz cumpleaños. ¿Cómo
Muchas
estás?
gracias.
Hola.
Hola. Happy birthday.
No se oye nada.
Ich höre, ich habe nichts gesagt.
No sé,
¿Me oyen? Hace un momento creo que me oyeron.
¿me has escuchado?
Antes me oyeron a mí. Ahora yo sí los oigo.
We cannot listen.
Yeah, there is no microphone. This is one inside there. So it's just an extension here, and we can listen him perfectly. Okay. So it's only, and I'm not sure that we should take it inside. Should not. So that's why I leave out here. ¿Escuchaste mi plática? ¿Todo? Buena base.
Se carga por USB-C, güey.
Hola.
El sonido está adentro.
I can hear you.
Because we need 5 minutes because we are still arranging few things. Okay, so the cake we put it here. I do not know if you can see it. It's here. So we have 3. Okay, one for Babashor, one for you, and one for Francois. But we are still arranging little bit of things.
I hear you. It seems you don't hear me.
Just a Thomas. No, please, Thomas. Hey, Thomas.
Hi.
Ja, Michael. Dresden. Oh, yeah.
I can hear.
Yeah.
You cannot hear me, Andy.
It's great to see you.
Good.
We should make it like this so we can see this better. Yeah.
Yes. At least I can see you now. At least I can see you.
I don't know. I think
Have a good time.
So you have the microphone is okay. If you go inside, you can go. Yeah, I'm sorry. Listen, why no, we just thought we being late because we wanted to keep you surprised. Oh, so at the very last moment we got this news that you had about no, right? And then we didn't get any answer. Oh, so that's what but if we buy it before, they will know somehow. Yes. Talia. I hope you are better than me in this. Oh, that's it. That's it.
Yes? Can you hear me now?
I need more. Yeah?
I
Can
hear you.
something. And what are subjects? There are much more subjects. Seconds. What is that? Oh, yes, yes. The point is, if somebody can you put something below and so that is up, you can see it better. Then, more. No, that's fine. That's fine. That's fine. Now he can see better. Okay. So we can invite this thing. So no, this is one way. Yes. It's in a form of negotiation. Yes, he can listen. We cannot listen him here, but we can come inside. It's yours? Hallo Thomas, herzlichen Glückwunsch.
Hallo, hallo.
Was war, sagte, dass mit der Hüfte alles ganz gut geklappt hat. Das freut mich total sehr. Hi, Thomas Seligman. I was calling you. There is no camera, right? Yes, you can see us. Well, you can see us. Yes, yes. You should take the compliment. Okay, sure. And ¿pueden cambiar la cámara?
If you want to say
Bueno.
hello to Seligman, you just use the mic.
Okay. Hi, Thomas. It's really wonderful to see you. I hadn't expected to see you this time anymore, but really wonderful that people think of us.
It's nice to see you. I think you don't hear me.
Yes, we do hear you.
We hear you very well.
Oh, you hear now. Good.
Yeah. No,
That's an improvement
it has been
because
arranged
some time
now
ago
in the
you couldn't
auditorium.
hear. But I'm happy that you are there, and I needed the operation rather urgently. I should probably have made it 6 weeks earlier than I could have been there.
Yes.
I wanted to wait until after the two events, but that turned out to be impossible.
Okay.
Hi, Thomas. Also very nice to see you.
Yes. So anyway, I'll see you, Jacques, here in 2 weeks or 3 weeks, I think it is.
That's right.
In 3 weeks.
Yeah, I'm looking forward to that.
Yes. So am I.
Hi, Thomas.
Well,
Okay.
hi.
So now we will have this short session to celebrate the birthday of Thomas Seligman, Francois Leyvraz, and Jacob Barbachot. So, hi, Thomas. Happy birthday. Hi. Jacob, hi, happy birthday. Francois, happy birthday.
Thank you very much.
So,
thank you.
First, I would like to invite them to, if they want to say something.
I can only say I'm very surprised by this very enthusiastic welcome. I hadn't expected that, but I thank you very much to think of me. Although I'm getting 70, so you can call me an old man, but I stay young forever.
Surely. Well, so thank you very much as well. I'm also extremely surprised, but and extremely overwhelmed. I mean, that was absolutely not what I thought, but it's absolutely great. Thank you very much.
Well, I also appreciate that at a distance you think of me, and I guess several of you will meet in 3 weeks here in Cuernavaca, and they particularly Jacques and Francois were so important to me and also to science, I believe. And as far as being an old man, I'm an old man. They're still young.
But Thomas, compared to Biden, you are really doing wonderful.
Well, I don't have so much of a weight on my shoulders.
Yeah.
So we tried to keep this thing surprise from everyone. Okay, we only 4 of us knew that. Okay, the organizers, and nobody else knew that. And we had to inform Thomas Seligman because when we come to know that he cannot come for his health, and so it was not surprise for Thomas, but it was surprise for others. So now, if anyone want to say anything, so I will forward the mic.
Yes. What's going to happen? So there is another conference. Which one? Tell us. Thomas will be the best person to say. About the event in Cuernavaca, which is going to happen.
Yes, but I don't know what I should say. So should I announce the event? Okay, so it's from 22nd to 25th of July, more or less, and it's about everything. Yeah, exactly. We have an organizer here. She knows. Yes. So the topic is random matrix theory, economics.
So I'm one of the organizers of the event, and it's from 22nd to 26th of July. It will be in SIC in Cuernavaca, and it's on random matrix theory. All different topics that are related to random matrix theory, and it's a celebration of 80th birthday of Thomas, 70th birthday of Jack, and 70th birthday of Francois.
So when is your actual birthday?
It
Well,
was on September
I
2nd.
might like to emphasize that the second event, was really organized by Juan and Thomas Stegmann, with a little bit of annoying interference from my part, but I tried to stay out as much as possible.
So Thomas, since I will not be there in 3 weeks, I'm very happy that I see you today, even remotely. I should be in the camera, yeah. And
Yes, that's better.
you might not remember, but it's about 22 years that you invited us with our daughter, age 2 at that time, I think, and we had a wonderful time in Cuernavaca, the family, and they all still remember that. And so thank you so much. And I guess also in the name of many, many others, you made happy scientifically and in other ways with your wonderful kind of activities there. And it's great that you're still there and active and we can see you today. And I hope you will have a wonderful celebration 3 weeks from now.
Thank you very much. And then in particular, give my greetings to your daughter. She probably doesn't remember, but anyway.
But she remembers the dog at the villa. Anyways.
Esta la mañana en que vengo a saludarte. Venimos todos con gusto y placer a felicitarte. El día en que tú naciste, nacieron todas las flores. Y en la fila del bautismo cantaron los ruiseñores. Ya viene amaneciendo, ya la luz del día nos dio. Levántate de mañana, mira que ya amaneció.
Thank you, thank you.
Thank you very much.
Las estrellas del cielo, tengo que bajarte dos.
The traditional song. The traditional.
Very traditional song.
I
A
know it.
lovely song.
I know it. I know the song.
So now we have 3 cake just outside, and we bought 3 cake in the name of Francois, Jacob, and Thomas. So that we will, I will request them to cut that, and that will be our part of our special coffee session, and then we will go for the poster.
Okay, thanks.
Thank you and enjoy the cake.
Great to see you.
Bye-bye, Thomas.
Bye.
Bye.
See you.
See you, Thomas.
See you. Thank you.